Morning, everyone. Thank you again for being here the second day. This is the first time that we have 2 days in this meeting, so for me I was interested to see how many people remains also the second day, but hopefully you have, let's say, enjoyed the first day. Honestly, when I designed the program together with my friends, Vanya and Giovanni especially, we decided on purpose to do, let's say, the first day some more transversal topics where people can be a bit more comfortable with AI in general and also with different thematics in more transversal way. And decided the second day to be a more, let's say, focused in what AI it's more advanced, let's say, in this case, because we will talk today about imaging, about multimodal, and also another special session. So let me say a few words. In this program, we had 2 keynote lectures. The first one was yesterday from Jacob, and the second one is today. Unfortunately, Mahmoud had a problem, for probably most of you know, some problems that are now in America. I mean, we don't have to, we know very well in Howard, and also, and he couldn't make, he has to, absolutely was everything planned to come here in present. But in order to have it anyway, because in Boston now it's very early, so we are 6 hours more. We are starting the first session, so now with the image part, where we will cover the digital pathology and radiomics, and then we will move to the keynote lecture from Faisal. He has done a pre-recording for the keynote lecture, but he will connect for discussion for more than 20-minute discussion, so he will connect at 6 a.m. there, and we can make all the questions. Let me remind that we have an hybrid event, so a lot of people are already connected, and please, because yesterday we did receive a lot of questions from the, if you want to remain anonymous, we can also remain anonymous, but please make also questions. And then I'm giving the floor to these men for the first session. Thank you.
All right. Thank you, everybody, for being here. Let's open the session on AI for imaging. I am Alessandro Cicchetti from this institute. I am a researcher and medical physicist working in the data science unit, and I will moderate the session with Giovanni.
Good morning, everyone. Welcome back to the second day of this Congress, and thank you, Arcela, to invite me to co-chair this session with Dr. Alessandro Cicchetti from Istituto Nazionale Tumori di Milano. I'm Giuseppe Viscardi, working as medical oncologist in a lung cancer unit in Naples. This session will focus on transforming power of radiomics and digital pathology. So let's begin with the first talk made by Professor Alexander Pearson from University of Chicago on digital pathology in clinical cancer care. Professor Pearson, the floor is yours.
Good morning. Well, it's a pleasure to be here. It's always great to be back. Thank you so much for having me. So I'm going to talk about today for focusing on digital pathology, and we'll talk a little bit about some of the applications that we are imagining for our care. These are my disclosures. So today I planned this talk to follow Professor Mahmoud's talk, so think of these as interplaying. I'm going to talk a little bit about digital pathology foundation models and the potential for those models in application, and you will hear more, I think, about the underpinnings of those models in Professor Mahmoud's talk in just a little bit. We'll talk about applications of foundation models for clinical care and for biological discovery, and then I'm going to talk a little bit about some of the freshest work coming out of our lab, which is quantum machine learning to understand multimodal data, including pathology. So I think as this, just over the course of this Congress, we've seen an evolution in how we think about training artificial intelligence models for digital pathology. And initially, we thought we would often directly train models using architectures such as convolutional neural networks, where we have pathology samples and we train a model to predict a certain outcome. I think that's evolved us, particularly in the last year, so that we now use a multi-stage approach where a vision transformer-based foundation model will be used to extract a set of language or descriptors from pathological features, leveraging potentially millions of images worth of self-supervised pre-training, and then a model will be fine-tuned to those images for a specific outcome in order to have a application-specific model. So just to say out loud, these vision transformer-based models reflect vast data exposure. So we're talking about hundreds of thousands of patients worth of data and millions of images. And these, in practice, produce a feature vector that describes the full variation space potential for that image concept. In my case, pathology, wherein a given image or region of an image is reduced to a 1,000-dimensional vector, which can be therefore processed like the omics of visual data, using analogous methods, for example, for what we've done for gene expression based data for potentially decades. And just in the last year, 2 years, we've seen an explosion in the opportunities to leverage a large number of different pathology foundation models, and I have listed them here. There's 15 or so, millions of images, many different papers, and a lot of benchmark work is going on right now to benchmark these foundation models. So just to serve as a background, this is the newest set of research-based hematoxylin and eosin content. And in terms of the state of the art for patient care, I think this is we can't have this lecture without mentioning this very recent FDA approval. So this is the Ventana TROP2 device that received FDA breakthrough designation April 28th, so during AACR. And this is the first pathology and immunohistochemistry AI-based companion diagnostic to exist. So it's a clinical predictor for TROP2 antibody-drug conjugates for non-small lung cancer. And I wanted to show this because I think, number one, it's a proof of principle that artificial intelligence has an existing place within the clinical care. And number two, just to illustrate some of the barriers to implementation. So I've put up on the screen some of the requirements to actually put this companion diagnostic into practice. It requires the TROP2 AI algorithm. It requires a specific Navify digital pathology image management system. It requires the digital pathology scanners, and it requires the Ventana TROP2 specific assay. So there's quite a bit of equipment and overhead in order to get at this, in order to get this FDA-approved asset up and running. And I think we're going to see over time an evolution, either investments on an institutional basis or an evolution in the amount of actual content required to run this assay. So this is where the state of the art is, and I think very exciting that this is now gained approval. But I want to talk a little bit about what we're expecting or some of the additional applications and how my lab is thinking about pushing the field forward. So I'm going to go through 3 examples of fine-tuning foundation models for clinical care and application. The first is HPV prediction, and I think we've shown for a long time that HPV status can be predicted directly from an hematoxylin and eosin immunohistochemical slide. Or, I'm sorry, hematoxylin and eosin stain slide. So as standard of care, I'm a head and neck medical oncologist, and so we typically do HPV detection for head and neck cancer subtyping via either immunohistochemistry, in situ hybridization, or viral genotyping. But we wanted to improve on some work that our lab did with Jakob Cather's group some years back to see if using more updated methods allows us the opportunity to get closer to these state-of-the-arts using a foundation model-based fine-tuning method. And so we combined some of the publicly available and private data sets for head and neck squamous cell carcinoma, and then we used a UNI foundation model-based feature extraction, and then trained a model to understand the landscape of head and neck squamous cell carcinoma. Now, importantly, we did something a little bit different in our training for this example. We trained effectively a linear trajectory, linear discriminant analysis that projects an axis of HPV-ness through the data. So understanding how to regress this high-dimensional expression of foundation models, and then we can evaluate effectively the principal component, the second principal component around that linear discriminant axis to understand all of the concepts of variation. This allows us, number one, to train a very accurate predictor, so the area under the receiver operator curve for our HPV detector is shown on the left, achieving near clinical immunohistochemical or genomic clinical accuracy. And it also allows us to express all of the variation within the given states. So we can, for example, then use an add-on generative adversarial network to provide visual explanations of all of the different imaging phenotypes of HPV positive or HPV negative cancers. And so shown on the bottom are some of the descriptors that pathologists, collaborating pathologists used to describe the axis or the most positive and most HPV negative states along a deep fake based axis of images. It allows us to therefore learn more about how HPV expresses itself. In the second clinical example, we wanted to see if we could interrupt oral precancers as they progress to cancer. And so, in collaboration with the U.S. National Cancer Institute, we trained, again, a feature extraction-based model with a very detailed annotation about whether an oral cavity precancer or high-grade dysplasia will progress to cancer or will not progress to cancer within a year's time. And we were able to predict this with very high accuracy, which we externally validated as well. So an area under the receiver operated curve of about 0.9 with a very high specificity. So this is really exciting. This high specificity test potential is really exciting as a medical oncologist because this tells us that this could act as a rule-in test, meaning predict those individuals that are most likely to progress and then intervene on them early before their oral lesion becomes a cancer, potentially with a medical or non-surgical intervention. Now, we're using the same sort of generative adversarial network-based tools to again improve our understanding of biology. So the performance of our deep learning-based predictor improves on what a human pathologist can accomplish with an AUROC gain of around 0.1, which is pretty significant in over the current standard of, for example, grading. But we don't have a language yet to describe what these additional patterns are. And so it's subtle, but if I play this movie again, you can see that we have, that there are morphological differences between the non-progressor states as we move to a progressor state, and then we move back to a non-progressor state within the movie. So we're hoping to, as we improve our model, hoping to improve and extract the amount of information that can be learned from these images. And we're also thinking about application. So this is the pathway study. This is results from a randomized placebo-controlled trial that I ran at the University of Chicago and was presented at ASCO last year, where we include a number of high-risk groups, including individuals with multiple previously treated cancers or pre-malignancy, and showed a PFS benefit for treating with immunotherapy in individuals that had, for example, multiple oral cancers that were likely to progress. So this would be an example of that high specificity, that rule-in test. What to do about it would be, for example, treat with immunotherapy. Or another study that we have ongoing at University of Chicago is this chemotherapy nanoparticle embedded patch that we can administer to an area of precancer. And in mouse models, we showed a very high rate of pathologic complete response. In other words, regression, chemotherapy-induced regression of precancerous states in mouse models. So we're currently in a phase 2, phase 3 trial at, it says phase 1, phase 2, but it's phase 2, phase 3 at University of Chicago, including for carcinoma in situ. And so what I'm hoping to do in the coming years is to pair this deep learning-based companion diagnostic with an intervention like this that selects those individuals that are most likely to benefit, and have a way to interrupt cancer before it forms. And the third example, starting to think about what we can learn from digital pathology-based deep learning. And so this is work from Bob Grossman's group here at University of Chicago in the US. And they did multi-omics analysis of TCGA patients. And one of the things that was most interesting to me as a head and neck medical oncologist was this area of squamous cell carcinomas that has a substantial amount of genomic overlap. So this is including, let's see, it's including copy number alterations, it's including RNA-seq information, all combined in high-dimensional space. And these areas of squamous cell carcinomas are overlapping, meaning that there is more shared biology for squamous cell carcinomas potentially than for some of the other cancer subtypes. So can we therefore leverage this kind of unique multi-cancer region to uncover shared genomic programs? And indeed, that's what one of my grad students is currently working on, is using this combination of multi-gene expression motifs and their expression in pathology. So we used a machine learning-based method called matrix factorization to cluster RNA-seq data, so the gene expression information, into a series of programs that were shared across squamous cell carcinoma subtypes. So these features were automatically derived with an unsupervised algorithm, but they span different tumors of origin. And when we look back at which pathways are enriched, we see that these factors tend to, or seem to segregate into some of the recognized cancer driver factors that we as cancer biologists understand. In addition, many of these pathways can be predicted directly from the digital pathology. So in other words, these unsupervised ML-based pathways can be predicted directly within the hematoxylin and eosin-based pattern, and then can be reconstructed, again, using generative adversarial networks to show relevant histopathological patterns. So for example, in this factor 11, which was putatively collagen and programmed cell death, our pathologists, when they evaluated, were able to identify nuclear, cytoplasmic, stromal, and lymphocyte-based patterns that were consistent biologically with the gene expression patterns that we expected to see. So this is us learning from pathology to explain shared motifs within cancer or across spanning cancer subtypes. So I'm going to pivot to some of the content we're currently working on to explain multimodal data. And so this is our group and others at University of Chicago are excited for the potential of quantum technologies as a disruptive force for biomedical discovery. So for those for it's been a minute since introductory physics, quantum mechanics are a class or a series of physical principles, some of which are listed here, which center around the duality of behavior of certain particles. So certain particles can behave as either waves or particles depending on the context, which drives phenomena like quantum tunneling, which is an intrinsic factor to causing mutations, for example, in cancer, different metabolism events, and many other properties that are intrinsic to our own biology. I'll give two good links here for quantum sensing and quantum computing for biological settings, respectively. But I wanted to talk a little bit more about quantum computing today. So quantum, and this will play into how we're thinking about processing data. Quantum computing, on the left, you can see what is a classical bit. So in a classical bit, this bit exists as either a 0 or a 1, and this varies this is different than a quantum bit, where a qubit or quantum bit is represented as some probability of states between 0 and 1, whose location can't be known with exact probability. So when you query a qubit, you have you are resulted with a probability of output. And this, if you're asking yourself, this sounds like a huge disadvantage for a computing task if there's this level of uncertainty. Well, you're exactly right. But the advantage for this uncertainty is that there's this property of quantum entanglement, which allows us to prepare, for example, 2 qubits with an intrinsically quantum-linked state called entanglement. And so via this entanglement, you can make circuits that act substantially more efficiently. And so for some tasks, a quantum circuit will experience an exponential increase in speed compared to a classical circuit. In other words, a classical circuit increases complexity with exponential cost, and a quantum circuit increases complexity with quadratic cost. So there's for some issues, for some computational tasks, a quantum circuit is going to be substantially better. So right now, the task at hand is, can we think of those areas where there's potential quantum machine learning advantage? And so we think that quantum advantage might occur when, number one, data is highly correlated with complex correlation structure. Number two, an optimization problem which scales exponentially with classical computing and quadratically with quantum computing, and where data is expensive, so there's not vast amounts of data. And so I think that multimodal data in cancer may satisfy all of these constraints. In the immediate term, quantum machine learning is limited, and the complexity and type of problems we can select are limited because there's limited access to quantum hardware with, say, 130 qubit or thereabouts computers available. The speed of data loading and limited circuit depth all limit our problem complexity. So we've selected this problem for this Wellcome Trust challenge where we combine DNA mutation data, gene expression data, and pathological image data, and have developed a hybrid quantum classical tournament algorithm, which allows us potentially to select which cancer subtype an individual's cancer comes from. And so while this is a very specific example, we think that this concept can be applied to a lot of different places. In our simulation studies, this cubic unconstrained binary optimization used to select which features from DNA, RNA, and digital pathology foundation models, we select a very small feature set, and we're able to show that there's a superior performance in the quantum selected feature set compared to classically selected feature sets, which validated an external data set, CPTAC. So this looks like incremental progress because it is, and even though it took about 12,500 GPU hours on one of the Department of Energy clusters, but we think that this shows extreme promise for applying quantum computing tasks to biology for advantage. So that I'll summarize that FDA breakthrough labeled AI devices are here. There's been rapid uptake in foundation model-based fine-tuning for specific applications within the last 2 years, and that quantum machine learning may provide superior data and analytic options for certain multimodal research contexts, including for digital pathology. So that I'll conclude, and thanks to my sponsors, to my labs, and to my collaborators at the University of Chicago. Thanks.
Thank you, Professor Persson. So let's move to digital pathology at work in action with a use case presented by Professor Julian Calderaro from Henri Mondor Hospital in Créteil. The title is Digital Pathology for Liver Cancer and Immunotherapy Prediction.
So first I would like to thank the organizers for this very kind invitation to discuss the role of digital pathology for as a biomarker for immunotherapy prediction. So I'm a pathologist mainly working in the liver, and patient with advanced hepatocellular carcinoma, which is the most frequent primary malignant liver cancer, have a very dismal outcome, and the standard of care is the association of atezolizumab with bevacizumab. Atezolizumab is an anti-PD-L1 antibody, as bevacizumab is an anti-angiogenic agent. So this is the standard of care, but unfortunately the responses are only observed in a minority of patients, and there could be some side effects. And we do not have any validated biomarker to identify the patient that probably benefit from this therapeutic. So there was this paper that was published some years ago, and they investigated the samples from the trial who led to the approval of the combination for patients with HCC. So they did plenty of techniques, RNA sequencing, multiplex immunohistochemistry, exome, and so on. And they identified a gene signature, which was called ABRS for atezo-bev response signature, that was able to predict progression-free survival in patients with HCC. Unfortunately, they could not predict overall survival. It's always very complex to predict overall survival in patients with HCC because they have also cirrhosis, so it's never very clear if they die from liver failure or from the tumor. So this was really pretty interesting and maybe the first biomarker, but as you may know, it's really hard to translate gene signatures into the clinics. And these technologies have been here now since more than 2 decades, and when they came up, they said, okay, pathologists, you are done. We will just put the piece of tissue in the microarray. You will have the diagnosis, prognosis, prediction, and so on. But 25 years later, we still have only one gene signature that is completely implemented in clinical practice for breast cancer, for prediction of recurrence after surgery. And I think this will continue to be this way because it's really, really complex to implement into clinical practice. So what we try to do is to predict this gene signature based on the H&E slides that we have for patients with hepatocellular carcinoma. It would have been better to predict directly with the progression-free survival as the label, as the outcome. Unfortunately, it's difficult to have large data set of liver biopsy of patients with HCC because there are some non-invasive diagnosis criteria, and not all patients that have the treatment have a biopsy. So what we did is first that we took a large data set of more than 300 cases for which we had the RNA sequencing and the slide. We trained a model, we gave to the model the value of the gene signature, and then we validated this model in more than 200 patients from my center treated by resection, and also 160 patients with biopsy samples from 2 different French centers. And finally, we validated the predictive value in an international cohort of 120 patients from Europe, America, and Asia, of really real-life patients that were treated with the atezo-bev combination. So this is the result of the prediction in the discovery series. So as expected, it's the discovery series, so the correlation is very strong. You can see the correlation coefficient, and you can also have this kind of heat maps where on the left you have a low magnification of the hematein and eosin section of a liver cancer, and you have the prediction heat maps. And so basically, briefly, the areas in red are predicted to overexpress the signature. We validated that in two different cohorts, another cohort of patients with resection, and very importantly, a cohort of patients with biopsy, because for patients treated with atezolizumab, most often we have only biopsy samples, so it was important to show that the model was able to work in a biopsy setting. So there was a drop in performance, which is expected. It's a validation series. Also in France, we are the only one in the world to add saffron to the staining, so we don't do hematine eosine, we do hematine eosine and saffron, so the staining is a little bit different. And also, we discussed also yesterday the problem of the explainability and the black box nature of AI, But we can first have a beginning of explanation. It's not full explainability by looking at the areas that are predictive of high ABRS expression. You can see on the left there are some tiles with a lot of blue dots, which are basically immune cells. And when you look at areas that are predicted to have a low expression of the signature, you don't have this type of features. So this was consistent because basically the immune gene signature was related to immune infiltration. Then what we did, so we were happy to see that the morphological features were consistent with what we expected, but you can go now a little bit deeper with molecular features, and you can do that using spatial transcriptomics. This is a new type of analysis, and I must admit for pathologists it's like Disneyland, because you can have the morphology, then you have the gene expression. It's really, really nice, quite costly again, but really nice. So what we did is that you have these slides, and you have a square where you put the tissue, and on the square you have 5,000 spots, and for each spot you get a gene expression profile, and then you can match the H&E appearance, the tile, with the gene expression profile that you get. And this is what we obtained on some samples, and you have on the left the H&E section, then the prediction it maps, so basically again areas in red are predicted to overexpress the signature, and you have the gold standard, which is the expression of the gene signature by spatial transcriptomics, and what you can see is that it roughly matches the heatmap prediction. So this was true when we did the statistical test, and there are different genes also below, so you can look at whatever gene is interesting for you and see where it is expressed. And then now there are these new kind of technologies. It's difficult to keep up with the evolution, which is very fast. It's the single-cell spatial technology. So now there are some technologies that allow you to have not a spot that is 50 micrometers, so you have several cells, but you can have almost the whole transcriptome at the single cell level. And this is an experience, some experiments that we did very recently. We do not have definitive results, but these are very nice images and just wanted to share them. So this is, you have on this image on the right, it's a tumor cluster with these pink colors and yellow staining. The stroma appears more in blue because you have the fibroblast stain in blue. So you have this first step of immunofluorescence for segmentation, and then you have some probes, and you can have a panel with more than 5,000 genes, and these are examples of apolipoprotein B and cytochrome, which are expressed by tumor cell of hepatocellular carcinoma, and you can have the spots where these genes are detected. You can go also a little bit deeper, and you really see here the tumor cells and where the mRNA molecules of these two markers were detected. So this is an example again with tumor cells of hepatocellular carcinoma. Then you can go also to check the stroma, for example, some collagen, which are usually expressed by fibroblast. And when you go again a little bit deeper, you can identify here on this image this elongated cell. I don't know if you have the arrow, but it's almost in the middle of the image, the cell that has the green and also the orange dot is a fibroblast that co-express different molecules of collagen. So you can then match also all these data with the prediction it maps and have some insights on what are the molecular features of the areas that seem to have an impact. So this is not full explainability, but I think with this kind of technology, we can make the AI black box a little more gray and maybe have some beginning of explanation. And I think it's very important to verify if the results that you obtain during this kind of test are consistent with, for example, the gene signature that you aim to predict, or the gene alteration that you aim to predict, and so on. So with that, I would like to end my presentation by thanking all the people that were involved in the work, in particular Xinre Zheng, who was my PhD student, who did most of the work on the prediction of the gene signature, and I would like to thank you for your attention.
Thank you, Professor Calderaro. Before moving to the second part of this session, we have a few minutes for questions from the audience, if there are any.
Hi, I have a question for Professor Pearson. Hi. I found really interesting all the parts about the quantum computing applied, in our work. I would like to know if there's a new technology that I think we will face. I hope ASAP. Do you think that this new technology will be applied more on, on old technology? For example, apply, we have now this problem of local minimum, and then we have to create a lot of problem in order to find the best global maximum. You know what I mean? Do you think that this quantum computing will be really interesting to be applied on these old parts of machine learning, or do you think that thanks to this problem, this new technology, will be really interesting to create a new structure on that? So what do you think it would be really interesting to apply in the next future? Thank you.
Yeah, great. An astute question. I think that one of the things I didn't say out loud, but that's really important to say, is that a quantum computing solution may be more efficient, but may also provide a different solution to a given problem. So we may be able, as you say, I think, to revisit some of the same questions we've asked of classical ML and ask them again with quantum ML and get a different, optimal solution, because it's a completely different paradigm. So I think this is very interesting. This is one of the things that my computational biology colleagues and I are interested with. I think that from a biological perspective, not everything is going to be better solved with quantum, right? Quantum is a totally different paradigm, and its optimality, especially with a limited amount of quantum computing infrastructure, is only going to exist in a certain set of problems. But I think that one of the other things that's happening in parallel is that we're improving in ways to sense intrinsic quantum biology. And I think that when we load quantum information from a quantum sensor onto a quantum compute hardware, we may see substantial efficiency gains from that perspective. So I think that, just to say out loud, there's two different aspects, at least, where we might see advantages that I'm excited about.
Thank you very much. I have another question for Alex, and about the use of quantum solution for feature extraction. Can you explain a little bit further? And you mentioned simulations, but I didn't get exactly what you simulate and what was real.
Yeah, so nothing is run on quantum hardware yet, right? So with in the next year, we'll have access to the IBM 133-qubit machine, and we will load this problem onto that machine. Everything I showed there was quantum simulation, and the QUBO algorithm uses quantum annealing for quantum advantage. So it's one of these contexts where we know it should be optimal, but that to simulate the results of the outcome requires, at this point, substantial GPU-accelerated simulation studies. So everything I showed was entirely simulated. But to achieve this empiric proof of what we hope will be shown once we load on quantum hardware.
Yes, I totally agree that to have simulations is to get ready as soon as we will have real machines to focus, where to focus and where to prioritize the use.
That's exactly right. This Wellcome Trust-based grant was entirely for this. Get ready, get biology ready to take advantage of quantum hardware that we anticipate will exist from 1 to 3 years from now. So it's all anticipatory. Like we're writing the software for the computer that doesn't exist yet.
Thank you.
Another question from me. Currently, there are different open source software ready for real-world implementation of digital pathology. Do you think there are a specific benchmark or validation step required before the integration in clinical workflow, or pathologists may be encouraged to develop a specific pipeline?
So this is an excellent question, and I think every pathologist is a little bit frustrated because we see plenty of things and plenty of publication, but the truth is in our pathology department, we don't even use now an AI model to count the Ki-67 immunohistochemistry. So there are different obstacles. The technology is not is there. AI is really no problem for that. Data is there. The main problem are really related to IT and how to have our, for example, in my department, an image management systems where I can plug an AI model and have the prediction in a timely manner in a clinical workflow. If I try to do it now, I have to export the slides and put it in another computer because the IT won't let me put my model in my hospital computer and so on. And you have all these kind of problems that prevent any implementation. So this was for the practical problems, and for the problem of academic model also versus industry model. I think this is a very important question, because if we don't allow academic models to be used, provided some quality controls, and we're working on that in the French Society of Quality for Pathology, we won't have models for plenty. We will have models only for basically breast cancer, prostate cancer, colorectal cancer, and maybe lung cancer, the most frequent. But for example, even for HCC, which is not a very rare disease, there is no company working on that because that's too small of a market. And that is, this is a very important thing, because all rare, or not very rare, but all not very frequent diseases and cancers, if we don't manage to have academic models, we will never see any benefit and we will never be able to use AI. So I think this is a major point.
Yeah. No, so Julien, comment for you. So what you show was an excellent use case, because I mean, as you know, immunotherapy has been used and has been tested in different type of cancer, Raquel, so we are using it. Obviously, the signals that we are seeing also in Dana-Farber group published a recent paper on digital pathology and immunotherapy in lung cancer. The performance and the metrics, I don't know if Evangelia is still here, I mean, are not so big. My question is, first of all, in terms of cohorts and prospective validations, since we discussed it yesterday also, biomarkers with Miaela, which are the steps that you are following? Because
so we have obtained funding like 2 months ago for the prospective validation of the ABRS model. We have 4 centers in France that have started to include patients. So I think in like maybe 2 years we will see what is the results of that. And also I think what is very, very important and probably not discussed enough in my opinion is some models you think they are low performance, 0.8, or you think it's not fit for the clinic because it's not enough. But I think taking account uncertainty, and I know you work on that, is very, very important, because I think the company don't realize that we use plenty of things that are uncertain in the clinic. For example, if I want to do a staining of a particular protein that is linked to prognosis, I get an intermediate result. So, okay, I don't take that into account for my diagnosis. And I think we can use also AI with that, and by playing with the thresholds of the model, we can say, okay, I will only give a prediction in 30% of the cases, but in this 30% of the cases, the prediction will be very accurate. And even if we have that, I think that's really a big step, because it will be very helpful for 30% of the patient. And I think we really have to take into account that.
Yeah, I totally agree. The uncertainty models are absolutely very relevant. I'm very curious, just another curiosity related to the prospective validation. So are you taking interventions, so decisions based on or just is the prospective one with prospective enrollment?
No, it's like what they call now silent clinical trial, something like that.
Silent,
we won't take any decision.
Observational one, okay, because it would be nice also, obviously, maybe in that case there are, we necessitate for a medical device or the algorithm to be approved, but still I think that prospective taking intervention would be also, I think further.
It's validated, that will be the next step. I think it was, even if we're very happy, it was maybe too soon to launch like an interventional trial. But if we really show that now it's validated in prospective staining, I think we will apply for really this time a trial with an intervention depending on the results. Yeah.
Alex.
Yeah. I just wanted to add one additional comment, which is about implementation. In the US, the rules have recently changed so that we no longer, to put a test into practice, we don't actually have to have an FDA-approved algorithm. A digital pathology biomarker, for example, is subject only to laboratory-derived test standards. So, like the same standards that apply, for example, if you're validating a new immunohistochemical assay, equivalency is the only standard based on the rules changed just this year that a digital pathology biomarker would potentially be held to at an institution-wide basis. So you could, as an institution, roll out a AI biomarker as institutional standard of practice, even if it hasn't been FDA approved. So I think this is going to be really, really exciting and important for moving digital pathology models into practice, but will be local instead of universal, which is the challenge.
This is great news, let's say, for you. I don't know what happens in Europe, but we can check a bit further this part.
More or less the same.
Okay.
I think we will be able to use that. And just to give an example, for the brain tumor, there is this methylation classifier, which now everybody uses to provide a diagnosis that is more accurate than our conventional diagnosis. And people, they upload their data to a server in Germany from the team of Heidelberg who did this work, and it's completely academic. It's not FDA approved, it's not CE marked, and everyone uses. So this is just an example that's something that is purely academic that everyone uses in daily practice. So it can be done, I think.
And my last comment is that it would be very nice to understand and to see if for future intervention clinical trials we can use the same biomarker, validate it within clinical trial, and just use it that further as in-house biomarker without CA. I don't know. That probably, I don't know if in that step we will need the CA market, let's say, because we are deciding a treatment. So that is. Checkpoint.
It's basic. I think it's going to be up to people in this room. As a community, we can decide what standards we're going to hold ourselves to. But like for some of these tests that are locally implemented, we can decide whether or not the performance, the validation criteria, and so forth are suitable for using on behalf of our patients. So it's an exciting and potentially risk-fraught opportunity, right?
Absolutely.
Just a comment, because I think in the lines you mentioned something that is a paradigm shift, which is not to consider the successful of a model just by the overall results, but by the capacity of highlighting some certain results and some, let's say, gray area where further examination confirmations might be needed. I think this is a huge change. And as a community, again, it's something that we might be able to highlight. Because at the end, maybe overall, you will never get to the 90%. But if on 60% you are really trustful, then we will work further with the others. But this is a change.
Okay. Oh, sorry, please.
Sorry, yeah, I totally agree, and I think that, you know, I'll give an example that Jakob told me, which was for his MSI model. You know, he went back and looked at discordant results for, you know, the false positives per the model, and those individuals harbored molecular states which were expressing a phenotype, but were not included in the MSI assay. So that it was actually the gold standard, the current gold standard was inadequate, and this was a chance for AI to teach us something about biology. So I totally agree. I think that
and sometimes models do converge. So they change by some decimal in the overall performance, but the real message is that on those patients, they all get the same answer. And so there is a very strong support for that subset.
And just a last comment, because we were involved in the study of Jakob, you know, because we had the samples that were POL-E mutated, so you get a lot of mutations also, and they were predicted as MSI, and so it's I think very, very important to go back to biology. So you take the false positive or the false negative that you think are mistakes, and then you go deeper into biology, and the significant proportion of this, what we call false positives, indeed could benefit from immunotherapy, and basically maybe the model is not MSI, but it's a high tumor burden, mutational tumor burden model, and I think this is really interesting.
Okay. So thank you very much for both of us.
Thank you to the speakers again. Now it's time to move to the radiomics part of the talk, and let me introduce Raquel Perez Lopez, a radiologist and leader in the radiomics group at Vall d'Hebron Institute of Oncology, and she's going to present a talk entitled "Where Are We in Clinical Cancer Practice?" Thank you, Raquel.
Thank you very much, Alessandro, for the kind introduction, and thank you, Arcela, for having me once again. You know, I love this meeting. Scientifically speaking, super exciting, but you also managed to create this warm and friendly atmosphere, which is quite unique. So thank you so much. Also, thank you for giving me the opportunity to show you some of the work we've been doing in the lab and some of the things we have learned when trying to extract quantitative data from medical images and to create new tools and new biomarkers that help us in the diagnosis and management of cancer patients. These are my disclosures. And this is the outline that I'll follow throughout my presentation. First of all, a brief introduction to radiomics. And then we'll dive into the proper applications of radiomics, giving you some examples for detection and also for predicting response, and also trying to understand earlier and better if a patient is truly benefiting or not from therapy. And last but not least, something that I think you will agree is very important, which is understanding if these tools are truly impacting the clinical practice. So with that, first I wanted to highlight something that it's very obvious for this audience, but I think it's important that we remember that medical images is a very powerful source of information. We can get in just a few seconds or minutes information from the entire body, three-dimensionally and non-invasively, which means that we can repeat this type of images throughout the course of disease, from diagnosis, staging, and again, understanding if a patient is responding or not. So when we put together these two things, the power of medical images and AI, we've been able to develop very useful tools for diagnosis and supporting our medical decisions. Second important point, we always talk or mostly talk about the applications of AI in standard data, and definitely AI is allowing us to extract very meaningful information and exploit as much as possible standard images like CT scans. But it's very important that we keep doing research in other lines of investigation, trying to get insights from the tumor from different perspectives, different angles. And for instance, I think it's important also to use AI to improve the image quality and to acquire advanced images like MRI and PET images in shorter time, so we can make this type of images more available in the clinic as well, and definitely also to post-process and extract quantitative data from the other technical images. And broadly speaking, there are two main ways to extract quantitative data from images. Classically, we've been using machine learning models from the so-called handcrafted to predefined engineered radiomics features. This is very well established nowadays. So there are some algorithms that allow us to extract quantitative data from every single voxel of the image. We can do something very simple like the maximum or minimum value of intensity or density of an area of interest, but we can also study things like the homogeneity or the heterogeneity of a tumor, and something that we radiologists love doing, adding in our reports this subjective way to describe tumors, if it's speculated or well-defined or ill-defined. So again, AI is allowing us, giving us the opportunity to move from this semantic subjective manner to describe things to robust numbers. And obviously, we can also feed the entire image into neural networks and let it to automatically extract some features from the image that may be associated to the endpoint that we are looking for without this predefined or hand-selected approach. But I must say that the vast majority of studies reporting radiomics-based biomarkers are based on this first approach of handcrafted radiomics, even in very high impact factor journals. The reasons behind are several, but something that, again, we have to bear in mind is the reality in our labs. So many times when we want to address a clinically meaningful question, the number of cases that we have in hands, it's relatively small, and we know that deep learning models tend to overfit. So we cannot use potentially those tools elsewhere because we don't replicate the same results. That being said, the field is evolving rapidly. So here we are, a potential solution for this problem, foundation models. We've heard Alex talking about it, and then we will have one of the godfathers of foundation models, Faisal Mahmoud. So I'm not definitely gonna go into the details, but basically we can train these AI models in huge amount of data. It's also true that this requires also a lot of computational cost, but we can get this array of features of the essence or the main characteristics of this type of data sets for then downstream task like trying to train a model that it's more clinically meaningful, right? So with that, let's move to proper examples and applications. And let's start from the beginning, cancer detection. So breast cancer detection is one of the beautiful and excellent examples in which AI has shown us that it's very useful and it's already implemented in many, many hospitals and clinics. So let me explain you a little bit about how breast cancer screening programs work. So we acquire thousands of mammograms daily in Europe, in the States, in Asia. And the guidelines indicate that 2 radiologists must assess every single mammogram. If both radiologists agree and they think that there is a suspicious lesion, the patient, or well, the woman in this case, will be recalled for further tests, and if there is nothing, the woman will go to a standard follow-up. The problem is that if they disagree, they have to meet and reach a consensus. As you can imagine, this is massive workload, very tedious task, And these computer-aided diagnostic tools are replacing one of those radiologists in many hospitals and clinics. And this is great because it's making this process much faster, efficient, therefore more affordable and accessible for larger populations. Similarly, in lung cancer screening programs, it's true that those programs are less broadly implemented, at least in Europe. But again, AI is particularly good at identifying patterns and identifying abnormalities, also in CT scans. So again, those tools are helping us to speed up lung cancer detection. You can see here, and it comes to what is important or what it's clinically more meaningful regarding one of these AI-based tools. So in this case, the tool doesn't work much better than a radiologist, but it speeds up the evaluation of every single scanner. And this is, again, very important. The risk of lung nodule to be considered malignant or not is based on very simplistic information, which is the size and the evolution of the nodule size over time. So this is, again, something that AI is very capable to do. But we can also try to use these tools to extract features that are, in terms of the heterogeneity and other aspects, deeper aspects of the nodule that are better associated with the risk of malignancy or not. And here you are, a bunch of different studies aiming to address this. We in the lab, following kind of the same approach, have tried to develop, well, we have developed a tool that called SALSA that enable us to fully automatically identify and draw the ages of tumors, in this case, in the liver. Why did we focus on the liver? First, because clinically speaking, it's a very important organ in terms of primary tumors like HCC, but also is one of the organs that tumors from other sites spread the most. And also for radiology, sometimes it's complicated to diagnose and definitely delineate these tumors. We managed to gather what I believe it's a large cohort of cases, more than 1,500 CT scans, and more than or almost 5,000 annotated liver tumors. And then we try different architectures to see which one works the best. And here you have some results. You have all the details in the publication. But just to give you some hints of the results, you can see here in the external validation, the detection performance is very, very high. And also the dice coefficient, so the overlap of the ground truth delineated by an expert radiologist and the one totally, again, automatically performed by SALSA overlap quite well. And also we try to understand the potential applicability of this tool and also compare it with the variability of the same radiology segmenting some lesions and several radiology segmenting lesions. And you can see here the variability of this dice coefficient. Even the same radiology segmenting the tumors, there is some variability, a bit higher when two different observers do this task, but very similar, and it mirrors the distribution, the variability by SALSA. And this is just one of the approaches that we can follow, try to explore the prognostic value of total burden of disease in the liver as a prognostic marker. And we are trying to expand this tool, make total SALSA, so potentially computing all the disease in the body automatically with different clinical objectives like evaluating in a better way response to treatments, for instance. We also developed this app in which you can upload a CT scan, and here you have the segmentation performed by SALSA in yellow. And here is one of our examples. So you have in red the manual segmentation. And we also asked some radiologists, blinded of course, to tell us which is the segmentations that they prefer the most. So you can, I don't know if you see my pointer. No, you know, okay. So you can see that in some cases, Some radiologists prefer the segmentation performed by the radiologists. Sometimes they thought that both were good enough, but in many cases, the radiologists making this assessment prefer the segmentation performed by SALSAM. So let's try to do something a little bit more complicated, which is characterizing tumor, diagnosing tumor. So once we see this big lump in the brain, the next question is, what is it? And based on perfusion MRI, so in this case, studying the vasculature of the tumor, and again, using AI to exploit and to get the most from this type of data, we develop a tool that help us to identify the 3 most common tumor in the brain. So GBM, glioblastoma, metastasis, or lymphoma, these 3 entities have a completely different treatments. So it will be ideal if in some cases, particularly in lymphoma cases, we could provide the physician a tool to support this diagnosis, so potentially in the future, patients will avoid having an open biopsy, which is, as you can imagine, complicated to do. We also developed the app, and it gives you a probability of each of these 3 tumors by voxel. So again, we think that this is an extra layer of information that gives us to the physician some degree of trustability. So if the tool gives you 90% of the voxels classified as one tumor type, I'm pretty sure that it will be right. But if it randomly gives different probabilities, I will definitely perhaps follow up the standard of care procedures to make this final diagnosis. Something even more complicated, predicting response to therapy. Clinically, super important, but where are we in this setting? So we and others have been working particularly in the field of immunotherapy, which is definitely an unmet medical need. You can see here a bunch of different publications over the last years, and you can also try to identify these phenotypes associated to the likelihood of responding to immunotherapy, the dispersion of the phenotype 3-dimensionally in the image, and also correlate with the histology, with the ground truth. Bottom line, the reality, when you have so many publications and so many studies, so many models, none of them is ideal. Again, we and others are trying to follow different approaches. Why not including and complementing this source of information with deeper insights of the tumor, for instance, with digital pathology. It helps. We have seen from, people here probably in the audience and other teams that when you combine clinical data with CT images, with digital pathology, the accuracies and the robustness of the reproducibility of the results is better for both in the settings of immune response in lung cancer, but also for predicting response to neoadjuvant therapy in rectal cancer. And this is, I think, a very promising line of research that, as I said, we and others are trying to follow. But once we have decided to give a treatment to a patient, we need to understand as soon as possible if they are benefiting or not. Long time ago, this was not a main thing, because when you can choose only between chemo, surgery, or radiotherapy, the fact that the patient progresses or not, I mean, ethically is important, but for the management, not that much. But nowadays, medical oncologists have a bunch of different therapy options, and we don't want to miss the opportunity to give the right one. As you can imagine, it's not surprising that some groups have shown us that we can capture some phenotypes in the tumor by imaging and track the dynamics, the changes of that phenotype upon treatment, and that correlates better than the standard response criteria like RECIST. But again, I think that it's important that we use these techniques also trying to get the most from all the type of images, and definitely multiparametric MRI can give us deeper insights into the tumor regarding the vasculature, the cellularity, the cell size, and in the field of immunotherapy, we believe this is very promising. We have managed to show the correlation with the histology, the ground truth in preclinical models. We have also applied this in a clinical trial that we have just finished, giving immunotherapy in advanced cancer patients and doing these multiparametric MRIs at baseline at very early time points, so just 1-2 weeks after starting treatment, and then after 6-8 weeks of treatment. And this is work in progress. We are analyzing the data as we speak. But we have also shown that in other clinical settings, like in the evaluation of response of sclerotic bone metastasis, like probably many of you know, it's again an unmet need in the clinic. We don't understand in for instance, prostate cancer patients that many times metastatize to the skeleton, and it's the only site of disease, and we have no clue if the patient is responding or not to treatment. You can see here, patient actually responding to enzalutamide, where the CT scan and the bone scan standard imaging don't change over time, and here a whole body MRI with diffusion weighted imaging with Dixon imaging, so we can capture also the amount of fat in the bone marrow, and this is key in this particular scenario. We can track the changes and see how the volume of disease decreases, how the ADC increases, so there is less cellularity in the tissue, and how the normal bone marrow in those elderly patients come back. And the combination of all these characteristics is a very good response biomarker in this particular setting. But how are we in terms of clinical applications? This is just a way to look at this, but if we see how many AI-enabled medical devices have been approved by the FDA, this is the update from August last year. There is a lot of them, and the vast majority are in the field of radiology, so using as the source of information medical imaging. Here we have pathology. It's a very hot topic, but still the amount of FDA-approved devices is relatively small compared to medical imaging, but the reality is that, again, the vast majority of them are for diagnosis, so the ones I show you using screening programs, and for treatment planning. And what does it mean? That those are tools that automatically segment normal organs, so they are very useful for radiotherapy planning, for instance, but we are not talking about tumor segmentation or prediction of response or prognosis or evaluating response in patients. And I also wanted to show you this study performed by the European Society of Radiology. So they circulated a survey, a questionnaire, through all the members of the association. It's very nice because they repeatedly in 2018 and 2024, so you can see the changes. And they asked them several questions. One of them, if they had incorporated and they were using AI-aided tools in their clinical practice. You can see that from 2018 till last year, the number of radiologists using AI has increased. Almost half of them say that they do use AI-assisted tools. But again, I wanted to highlight this. Most of them is for, again, a screening program, post-processing of the images, and so on. And just a detail, a minor detail that I wanted to pinpoint is that from all the people they sent the questionnaire, only 2% of them responded. So I think we may also have in mind that there may be a bias, and probably those that responded are the ones that are more interested in AI. So I think that it's obvious that there remains a big gap between research and the clinical application of these tools. The reasons behind are multiple, and probably more will come to your mind. And I just wanted to highlight this clinical validation, which I think is key for particular tools that may be useful, I mean, for taking clinical decisions. I think this is one of my last slides, so I know I'm running out of time. Thank you for your generosity. So, no. I prefer to finish, if you don't mind. Just the two minor comments. So this review of studies of clinical trials addressing the relevance of AI-aided tools in the clinic from January 2018 to November 2023, only 86 clinical trials were evaluating AI-aided tools, only 59 regarding medical imaging, and you can see that most of them involve only one center and relatively a small number of patients. So I think it's a key issue to bear in mind and to make the effort to move this forward and to collaborate together in these multicentric prospective trials, and definitely not forget, and this has been also mentioned yesterday, the importance of using real-world data for validation. But obviously we will face some challenges, and here I show you this review in which we mentioned the main ones when we use real-world data regarding images and how to address them. And with that, I just want to thank the radiomics group, amazing team of people that has done most of the studies that I've shown you, collaborators, the people that give us the money to keep doing this, and thank you for your attention.
Thank you, Raquel. And now we have the use case. Let me invite on the stage Luca Boldrini, radiation oncologist from Policlinico Gemelli and head of the MRI-guided radiotherapy unit and radiomics research program at Policlinico Gemelli. Thank you, Luca.
Thank you. Thank you so much, Alessandro. Thank you, Ursula, for the kind invitation. It's a pleasure to be here representing my discipline, radiation oncology, which is pretty rich of AI applications into clinical practice. I do not have any conflict of interest rather than being a radiation oncologist for this talk. And I want to briefly recall to you the guiding principle of radiation oncology. How does it work? It's a therapeutic approach that is based on effects of ionizing radiations in eradicating cancer cells. In general, generally speaking, most tumors are radioresistant if they're not hit by the radiation beam, and some tumors or part of them are radioresistant even when they are in the treatment beam. So we just needed to understand how to address our beams in the most appropriate way. And the most immediate answer was to do it with imaging. We do use a lot of different kind of images throughout the patient care path in radiation oncology, both offline or online. When we say online, we say when the patient is on the treatment couch of our linear accelerator. And these images can be read with, of course, therapeutic intent, image-based characterization of the tumor, the gross tumor volume and the other volumes of therapy, or with a background role for personalized precision intervention. And this is something that is becoming way more common day by day. In our center, we always have seen images as a support for decision-making in radiation oncologists, and one of the most studied field here in Gemelli is rectal cancer, locally advanced rectal cancer undergoing neoadjuvant chemoradiotherapy, and this is more or less the story of what we have done in our lab, starting with the very first experiences in 2017, in which we developed some predictive model based on staging MRI radiomics to predict the pathological complete response. Then you see throughout 3 years that performances grew, and we started to do different studies using fractal dimensions and comparing different field strength. But then something happened in the community because MR-Linacs popped out. MR-Linacs are hybrid machines that link together, that merge together as MRI scanner. You can find in the marketplace 0.35 Tesla and 1.5 Tesla MR scanners linked with linear accelerator. And we did a very first Pathfinder experience using MRIs from 16 patients. It was a very low number, but was at the time the largest cohort available in the world, with 26 images per patient, so MRI that were used as positioning image. And we started studies how the tumor was changing imaging for the very first time using everyday MRI. We then applied some radiomics on it, understanding the role of possible different features, and you can see here that two of these features were particularly significant throughout the whole path of care, and the highest significance was the second week of treatment, with a total dose of 22 grays was delivered. Here you will see also the differences between a responding patient and a non-responding one, in which we do have the regression of the tumor in the anteroposterior axis. This is what happens in terms of quality. Standard of care with a COMBIM CT, where the patient is treated in the largest majority of the centers in the world, and MR-Linac, in which you clearly see the gross tumor volume in the mid-rectum. So having this kind of quality allowed us also to test other hypotheses using, for example, early regression index, which is something that we owe to the group of Claudio Fiorino in Ospedale San Raffaele, and that we tested for the very first time, thanks also to the help of some American centers, using everyday MRI images. In this way, we obtained a very robust model that was predicting response. This prediction means personalization of dose distribution, because we were able to understand which patients were not responding to therapy and therefore react during chemoradiotherapy itself. And this is the rationale that through the Thunder 2 trial that is now that has now completed the enrollment, which stratifies the patients using a very simple early regression model that uses first-order morphological features at the second week of treatment. If the patient is considered a responder, then he goes with the normal pathway of care. If it's considered a non-responder, then we add a third level of dose, something that has been doable only with the use of hybrid MR-Linacs and the online adaptation solution. You can see here the three level of dose. Light green is the large volume that gets 45 grays in 1.8 fraction. Light blue is the normal high dose volume, the standard of care that reaches 55 grays in 2.2 fractions. And then you see the gross tumor volume, something that you cannot do very accurately using a COMBIM CT based X-ray based Linac, but with MRI you see it very clearly. And this goes up to a third level of dose in the non-respondent patients, up to 60.1 in fractions of 2.3, starting from the second week of treatment. The rationale is pretty clear. If you go high with the dose, then you expect a higher rate of response. And thanks to the online adaptation, we can cover the gross tumor volume very precisely. And also during the irradiation, we have a CineMRI with 8 frames per second that has a direct gating approach on the lesion. If some bubbles of air or the bladder fillings change, the machine stops automatically in 0.4 seconds. And this means that the safety of the patient is ensured. The first analysis of toxicity profile were very positive. We just have one toxicity event of grade 3, and ironically, it was on the patient arm that was not doing the boost. Just to give you some numbers, in literature we do have rates that go up to between 10 and 20% of grade 3 toxicity, meaning that the online adaptation and the better visualization of the target volumes has a direct consequence in terms of toxicity mitigation. And then we had great results in terms of response increase. We are used to have institutional course and literature data of complete response ranging from 20 to 25. In this specific cohort of patients, we reached more than 40, meaning that of these 43%, we have almost 20-25% having a complete pathological response, and also an increasing number of patients that are not undergoing surgery and watch and wait. Starting from this evidence that was done, as I said, only during the Thunder 2 trial, we added, thanks to the support of the Next Generation Clinician Scientist grant which is made available by IRC, which I, of course, very thankful, we added some other information, and we are currently running the moreover study, which has 2 steps. The first one is to enrich the image-based prediction model with other information, which are microbiota and circulating tumor DNA, complete sequencing of using the TSO panel of more than 500 genes, and then the development of new response-enhancing strategies that are not only triggered by image analysis, but also by information gathered from ctDNA and microbiota. And we are currently concluding the first phase of enrollment in this first observational step, and then we will launch in the remaining 2 years the interventional prospective validation, hoping to spur surgery and give more quality of life to our patients. So as you can see, AI is the common thread of what we do in terms of better target, a new way to understand imaging as target provider for radiation oncologists, and this will not be doable without the help of all the radiomics lab in Gemelli. You can see here all the stuff. I am the only medical doctor, but the continuous exchange that we have in the lab makes available a lot of common growth, and we love working together. Thank you so much for your kind attention.
Thank you, Luca. I invite both the speakers on the microphone, and we have now the discussion, so please, any question from the audience, maybe a couple of quick questions. We have one on top. Microphone over there. Where? Alberto, se può alzare la mano, please. Thank you.
So, thank you for the presentation. It's a question for both of you. So I'm also working on the radiomics and deep learning part. And my background is actually radiation oncology. So I think the world is split into 2 parts, right? The part where you have high quality data and temporal data, which is example of MR, LINAC data, and MR, you show the habitats imaging, you can do that pretty easy in MR. And the world where you actually want to predict things before treatment, you usually have a low dose CT. If you're lucky, you might have a contrast enhanced CT. So I think, well, Luca, what you show is that, when you have high quality data and you have temporal data, and I think if you look at the apparent diffusion coefficient maps, already looking at the changes in diffusion coefficient will be predictive for response to treatment. So you won't need such a complex AI, right? You might feel radiomic feature, but mainly first order, a bit of texture feature. You saw the change in gray level, so they change, let's say, in complexity of the tumor. However, if you have computed tomography, you have to think about the complex AI, and I think it's because the quality of the image is so low. So the question for you is, should we focus on building networks that are more and more complex to recover, try to get complex features, or should we focus on generative AI and try to produce synthetic data or enhance image quality and then use an already existing algorithm, or maybe focus on easier features?
Yeah, very, very good comment and slash question. I totally agree with you. I think I tried to highlight part of your comment during my talk. So definitely there are different approaches to the way we try to develop biomarkers from medical images. So from CT scan, I wouldn't say the spatial resolution is much lower, but definitely we don't understand, fully understand the biology behind those features, and AI is helping us to extract kind of more complex, phenotypes or from those images that may be or not potentially associated to the clinical outcome. In terms of MRI, and this is one of the fields of research in my lab, you have a much closer biophysical explanation of what you're looking at. Therefore, you don't necessarily need to extract those more complex features from the image, but just directly, as you were saying, try to compute voxel-wise biomarkers or average those values from the area of interest. So I don't know if I partially at least responded to your question. And Luca, I don't know if you want to add something.
Yes, thank you. I think that the answer is closely related to the research question that you're considering. Like, for example, for radiogenomics purposes or for tumor characterization, I would rather go with synthetic data. Well, for response assessment and prediction, I would rather go for longitudinal, so better quality ones. I have to say that MRI, of course, can have a huge amount of data with them, but it depends also the kind of MRI and anatomical site. As you know, from your background, we have two different kind of MR-Linacs, and the field strength is particularly important in terms of what you can get from the images. I mean, having a 0.35 Tesla means that your diffusion-weighted imaging, which is doable, we already demonstrated and tested it, could be of lower quality rather than a 1.5. This is pretty evident, but then that you have shorter sequences so that you can acquire them in breath-hold conditions, something that you will not be able to do with 1.5 Teslas in moving targets. So there is always a balance that you have to find. And in this way, my suggestion is having very clear the research question, just to address the sample size calculation, that for characterization something which is pretty unknown, like radiogenomics applications or more advanced tumor characterization, synthetic data will be very helpful, I believe, especially with CT environment. I personally do not see still very robust models doing synthetic MRI images, especially with quantitative imaging, but I think that we will be there in 3 to 5 years. Yeah.
And if I may add something and build up on the concept of the applications of AI in MRI as well. I was telling you that it provides direct explanation about the biophysical meaning. But many times that requires that we perform very long protocols, rich protocols that in the clinic are not feasible, and definitely also AI plays a crucial role here, either by with generative AI generating the images that you will acquire, the signals you will acquire from a more simplistic protocol, or directly predict the biomarkers that you can extract from those complex protocols.
Okay, and there are other questions from the audience? So maybe I can go with a question from my side. Luca, you mentioned the radiogenomics, and actually I think is a good example of exercise for a radiology task. I mean, are we really ready for that kind of step from imaging to genetic data, or with the new, let's say, potential of MRI techniques, we have to go and address now issues like related to tumor microenvironment and to understand who are the better responders, considering that maybe the characteristics of microenvironment are not just related to the phenotypes, but even sometimes to characteristics of the patient himself.
Yeah, I totally agree with the last part of your comment. So there is, of course, some phenotype correlation that we need to still understand and describe that may allow us to identify some common phenotypes in patients that bear a specific mutation, something like that. So this is also why in the moreover trial we are sequencing the patients, and we are also sequencing the patients in 3 different time points. Before the start of the radiotherapy, at 22 grays, which is the most informative fractions thanks to the studies that we have conducted together before, and at the end of the chemoradiotherapy treatment. This also allows us to understand if there is a selective pressure in the cell populations that, let's say, leaves a niche of radioresistance and whatever. And we are opening as radiation oncologists a brand new meaning for radiogenomics. Radiogenomics is not only the link between an imaging phenotype and a mutation, but this is something that will for sure condition the prescription. We are talking in our community about genome-adjusted radiation therapy, radiation dose, GARD, which is the acronym, which will be in the next years one in paradigm for dose prescription. 50 grays delivered to a patient bearing a mutation X are not the same of 50 grays delivered to who is bearing the mutation Y. This is something on which our community overlooked in the last decades. We just know where not to deliver, just when you have ataxia, telangiectasia, and all the conditions that make complications more severe. So we know where not to go, but we didn't explore that much where to go. And this is something that we're currently doing. So I'm very excited on the next steps. Yeah.
I can just briefly add something just to wrap up. But basically, the literature up there have shown us that for specific mutations, definitely digital pathology and the spatial resolution that it provides is more capable to capture those phenotypes associated to the changes in the whatever it is, cellularity, shape of the cells of the nucleus. While for clinical outcomes, medical imaging is slightly better, probably because it's capturing the what's going on in the whole body. So definitely those are complementary sources of information. So in terms of radiogenomics, when trying to predict a specific mutation, I think it's complicated, but what images can provide is a phenotype that is associated to the secondary effect of that mutation, like in BRC mutation, the aggressiveness of the tumor, or the sites where the tumor has more probability to widespread.
All right, thank you to the speakers again. Let's close the session. Now we move to the remote session. Thank you.
Okay. So, okay. So here we are. As we said, now we will have the second keynote lecture session. I am a bit sad that Mahmoud is not here in presence, but probably he is already connected. However, for connection, let's say, to be sure that everything is smooth, we have pre-recorded. So now we are going to launch the pre-record of the talk, and then the discussion. But before that, I want to introduce my co-chair, who is Professor Giacomo Boracchi. He's a professor in computer science at Politecnico di Milano and a big expert in image, but not only in medical images, also in other type of images. So, your words.
Yes. Thank Graciela for introducing me. Very nice to be here. In our group at Politecnico di Milano, we deal with imaging at different level, both of computer vision side and say image processing side.
Thank you. So the talk about Faisal Mahmoud will be focused, as I mentioned before, based on his, probably you all, not probably, you all know him. I mention him, I think, in every presentation that I do everywhere, because he is the father of digital pathology in cancer, and especially based his lab in foundation models in pathology. In fact, he is associate professor at Harvard Medical School on pathology. He is a computer science by background, by the way, and has a big lab working on that, and I think he is the most influenced as a researcher in AI in the last 2 years. He's also co-founder of one of the most relevant co-pilot in digital pathology, which is called Model AI. And I'll give him the floor now for the presentation.
Thank you so much for inviting me to speak today, and I apologize for not being there in person. Today, I'll be talking a little bit about some of the work that my group has done recently around multimodal foundation models, generative AI, and agentic AI for pathology. These are my disclosures. My group predominantly works on the analysis of digitized pathology glass slides, which have really been the cornerstone of biomedicine for over 150 years, but have only recently begun to be digitized and computationally analyzed. Once these images are scanned, they can turn into very, very large images that are more like satellite images and harbor information at many different scales. And the goal of our work predominantly is to go from these images to everything in the red box here. This includes early diagnosis, prognosis, prediction of response to treatment, and outcome prediction, as well as integrating with other kinds of modalities to achieve all of that. The most commonly used framework for parsing this kind of data is multiple instance learning, and this is really a time-tested framework and has been adapted by a lot of different methods and tools, and has been applied to almost every disease model and organ system at this point. But the overall workflow is such that once your glass slides are digitized, you segment out the tissue region and you patch it into smaller patches because the slide itself is difficult to process altogether. Once you have those patches, we extract rich feature representations from these patches, and then we aggregate this information to a slide level representation followed by a prediction. And you can pose this setup for any kind of predictive analysis, which includes disease detection, subtyping, survival and outcome prediction, treatment response prediction, anything that you essentially have a label for. There are some issues with vanilla multiple instance learning that often uses a max pooling based aggregation function, that it can be inherently data inefficient. So back in 2021, we did some work to try to make multiple instance learning a little bit more data efficient by using attention, as well as using pre-trained encoders and extracting features from those encoders rather than end-to-end training. So we did make the code and models around this publicly available, and these tools have been extensively used by the community. A few examples that we worked on included cancers of unknown primary back in 2021, where we tried to see if we could predict origins for metastatic tumors and cases that have been assigned a diagnosis of cancer of unknown primary, using multiple instance learning posed as an 18-class, essentially a multi-class, multitask classification problem. We also applied this to other applications, including for endomyocardial biopsy assessments and for integrating histology and molecular data to see if we can predict better outcomes and separate patients into distinct risk groups. More recently, we have worked on foundation models. So some of our earlier work focused on using ResNets that were trained on ImageNet, and more recently we have started to use self-supervised learning. We started experimenting with self-supervised learning back in 2020, and in 2021 we published a NeurIPS article around it, showing that self-supervised learning for pathology could really improve representation. But last year we published these two foundation models, UNI and CONCH, and UNI is really a foundation model that is predominantly trained on lots of diverse pathology images, and CONCH is a foundation model that's trained by contrasting images with text information. So we made both of these foundation models publicly available, and they have had a lot of traction, and they've been downloaded over 1.4 million times over Hugging Face, around 1,400 different institutions. And one reason we think that this has been the case, we didn't even know that this many people were interested in computational pathology, but one key reason we believe is that because pathology is so foundational to any question that you can ask in biomedicine, and pathology data is often there and available and is increasingly being digitized, that if you have rich representations for this data, or you can encode this data into lower dimensional representations, it can easily be incorporated into any question that you're posing as a machine learning question, any biological question that you're posing as a machine learning question. And this is just a distribution of all the studies that have already used these models in the span of the past year. So key takeaway message is that well-trained self-supervised models extract rich feature representations that can then be used for lots of different downstream tasks. Both of these models were extensively tested on lots of downstream tasks. Besides text, we also have lots of other information corresponding these cases available to us. As an example, we would have molecular gene expression, NGS assays, as well as immunohistochemistry or other special stains that are available corresponding H&E images. So with CONCH, we showed that you can contrast with text to improve the image representation. In some of these subsequent studies, we have shown that you can contrast with this additional information to achieve even richer feature representation. An example of this is this study, which we call Madeline. This was published in ECCV last year, where we were trying to contrast between H&E and corresponding special stains and immunohistochemistry to see if we can improve the representation, which can then be applied to a variety of different downstream tasks, including survival, outcome prediction, as well as for immunohistochemistry analysis. And if we can contrast with the with IHCs and special stains, we can also contrast with molecular data, and that's what we tried to do in this study, which really was a toy example just by using the TCGA to see if we can contrast between H&E images and corresponding transcriptomic information to see if we can improve image representation that can then be applied to a host of different downstream tasks in a few shot settings. And one thing we realized that the performance improvement was really drastic in comparison to contrasting with other modalities that we were considering, giving us an early indication that contrasting with molecular data could lead to rich image representation. So that's what we decided to scale, and in scaling this, we used all of the data that was available to us from the Dana-Farber Brigham Cancer Center. There's a large NGS assay called Profile, as well as all the data that we had available from MGH, which is including a transcriptomic assay, and we contrasted against this data. So it's important to remember that we are contrasting against this data, and we're not fusing this information, which means that we can have multiple pipelines that that effectively encode this data and contrast with the H&E images with the goal of improving image representation. And in doing so, we were able to improve the image representation enough that we started to get a significant performance boost on some of these more difficult tasks like treatment response prediction or IHC quantification, many of which had limited data available to begin with. So the key takeaway message is that multimodal foundation models improve representations for all modalities, and multimodal foundation models reduce the amount of net data needed to achieve equitable performance. We had a parallel study called Titan, where we were using over 350,000 slides in a self-supervised setting, followed by contrasting with text. And in that case, we needed about 350,000 slides versus only about 50,000 slides in the case of threads to achieve an equitable performance. So multimodal representation learning does reduce the amount of data required to achieve equitable representation. So with all of the previous studies that I described, we essentially established that multiple instance learning is the sort of a very foundational concept in pathology, and then feature extraction is perhaps the most important component within multiple instance learning, and that feature extraction could be accomplished, of course, by using pre-trained encoders using self-supervised learning, and we showed that you can do that in a patch setting using unimodal or multimodal data. And as you use more and more multimodal data, your representations get richer and richer. But effectively, we've established that you can project this data into lower dimensional feature space, while ensuring that those features are rich enough to be representative of the actual image domain. Once we have done that, the next obvious step to us was to start building some kind of a chatbot or a vision language model where we can start asking questions. So that's what we did in this study from back last year. And the philosophy behind this was that pathology images are large and hierarchical and harbor information at many different scales. However, the only labels that we have available corresponding these images are at the level of the slide or at the level of the case. But to build a generic universal chatbot that can cater to every level of abstraction, that is the ability of the user to ask any question, whether it's at the level of the region, at the level of the slide, or at the level of the case, we need very fine-grained morphologic descriptions at all of these different levels of abstraction. And that's what we try to effectively achieve in this in the study by collecting a lot of data, including with manual data curation, utility of training materials that are often used for resident training, and eventually curated a large instruction data set that was used to train this model. At the time, we had about almost 500,000 instructions, but more recently we've scaled this to really 5 million instructions that are used to train PathChat. And the goal here is really simple. We want to have a single multimodal large language model that can cater to all of human pathology. And why do we believe that this is possible? Companies like OpenAI are trying to build these large high capacity models that cater to human knowledge and human information. Our goal is much more specific. We're trying to build a model that would cater to effectively just knowledge corresponding human pathology. So if it's possible to build a single model harboring all human knowledge, definitely should be possible to build a model that can harbor all pathology knowledge, which is only a subset of all human knowledge. Once the model was trained, we could then start going in and asking questions about specific regions within the image. Like in this example, the user asks questions about what type of tumor it is, followed by questions around specific morphologic regions within the image, and then eventually the chatbot can also produce a pathology report. More recent versions of this chatbot can do a lot more. They can answer questions at every level of abstraction, which includes the region, the slide, or the entire case, as well as interfacing with other kinds of multimodal data. Another example of this is its utility in low resource settings. So some foundations that we do some work with are very interested in using this kind of a chatbot in low resource settings where it's often quite difficult to track down the patient once they have left the hospital, and if the cases are sent out for consult as a consult, they can take a really long time to get back, which often means that they never are able to track the patient back again. So having some kind of an indication about the interpretation of the pathology slide while the patient is still in the city or in the regional proximity of the hospital is quite valuable to these foundations. So we are looking into deploying this in lower resource settings as well. The next thing I want to chat about is agentic AI for biomedicine. So I guess 2025 is a year of AI agents where everybody's talking about building these generalist agents that can do a lot of things for you. Computational biomedicine is really ripe for the utility of such agents, because what we're doing in computational biology quite often is bringing new kinds of data to existing tools for discovery. We do develop new tools, but typically it's bringing a lot of new data to existing computational tools that are out there, and biomedical discovery is inherently multimodal and multidisciplinary and requires diverse use of tools and skills. And what we want to see is it possible for us to use simple text prompts, which can then be parsed into instructions that can then be, that this agent can effectively use and invoke some of these individual tools effectively on its own. So for that, we need some kind of a planning agent that would plan out what the plan would be based on the text prompt, a DAX scheduling unit that would schedule which tools to use and when to parse through these different tools, as well as interacting with a coding agent, a language agent, and a visual agent. A visual agent in this case could be, for example, the PathChat tool that I showed that does interpretation of some of these images, as well as linking back to literature. So this entire workflow would effectively provide us with a blueprint for how these agents can be used for biomedical discovery to accomplish certain tasks. And I do want to show a small demo for this. So in this case, the user is asking the agent that I have a cohort of responders and a cohort of non-responders. Is it possible for you to effectively go and train a model that would tell me how morphologically distinct is the responding cohort from the non-responding cohort. So the model essentially makes a plan which entails segmenting all the tissue regions, patching all the slides, extracting features, and then once the features are extracted, training a model that would effectively tell us that how morphologically distinct these two cohorts are. And once we know how morphologically distinct they are, then we can interpret more from the model. So in this case, the model AUC is about 0.855, maybe not good enough for clinical utility, but should be able to give us some morphologic understanding for what is the distinctive feature within these images. And you can start by looking at a heat map, which is very, very difficult to interpret because it's more like reading the tea leaves, and you can't really tell what the model is paying attention to across the entire test set. A much better way might be that you can ask PathChat to look at all the top high attention regions across the entire test set and give a report for what the model predominantly pays attention to. And in this case, the user says that it's essentially, PathChat says that it's essentially paying attention to the inflammatory response, necrosis, fibrosis, and so forth. And then the next step we could do to get further enhanced interpretability is to say that, well, can we extract all the handcrafted features from the cells and see what are the differences between the responding cohort and the non-responding cohort. So this, effectively entire study is run entirely through an agent. The next thing I want to talk about is moving from 2D to 3D pathology. So pathology is inherently three-dimensional, but we often look at a sampled set of the three-dimensional tissue, and for many diseases, interpretations, the 2D tissue might be good enough, but we know that for some disease models, the diagnosis can vary depending on where the tissue is sampled from. And over the past few years, there's been just tremendous progress in imaging technology to image these tissues, but there's been limited computational pipelines that have been developed to interpret these very large images that might be difficult to interpret manually, essentially to discover effective biomarkers or companion diagnostics that could be used corresponding drugs, as well as for potential clinical utility down the line. So that's what we tried to address in this study from last year, where we used prostate cancer samples, and these samples were imaged at the University of Washington in Jonathan Liu's group, as well as at the Harvard Nano Center using a micro CT scanner. And we basically extrapolated the work we had done on multiple instance learning and effectively scaled it to 3 dimensions, which made everything very, very computationally complex, but the basic fundamental idea remains the same, that we extract rich feature representations that they can aggregated, followed by a prediction. So this was a Cell article from last year. Key findings included that we can separate patients into distinct risk groups a little bit better when we use the entire 3D tissue volume rather than using a small region within the tissue. Is just an example for what happens when you use the entire tissue volume versus smaller regions, both for an open top light sheet microscope as well as for microcomputed tomography. And then, of course, you could look at the nice heat map in 3 dimensions to analyze and assess what regions the model is using in making some of these classification or outcome prediction determinations. Okay. So another thing I want to touch upon before closing is AI-driven 3D spatial transcriptomics. So this is a very recent project, and it's still really work in progress, where the goal is to see if we can use tissue samples that have been imaged using 3D imaging and minimal spatial transcriptomics together with AI to predict what the entire 3D spatial volume would look like. And in doing so, we make use of pre-trained models that are trained on lots of data from the same tissue type, followed by some fine-tuning on on data that comes from within the same patient, essentially in-patient fine-tuning to make the model effectively produce much better interpolatory results across the entire 3D tissue volume. And we showed that we can do this. This is a preprint where you can go and look at some of these extensive results around the examples that we have in there. It often picks up features that it should be picking out, and we are doing some much more extensive validation on this, including adding an additional imaging modality, so it's sort of modality agnostic, as well as looking at other kinds of interpretation to see if it picks up on similar morphologic features. And then you can also go in and start looking at 3D spatial transcriptomics that are essentially inferred and predicted using machine learning through a viewer. So key takeaway messages from my talk: just foundation models are the backbone for modern AI in biomedicine, encoding data into meaningful representations. Diversity of data is much more important than the quantity of data. Multimodal foundation models improve representations for all modalities used in the training. Multimodal foundation models reduce the amount of net data needed to achieve equitable performance. Then foundation models are essentially, this is sort of final word on foundation models, that diverse data and multimodal data builds the strongest foundation models. And autonomous agents discover from data, make use of foundation models, test hypotheses, and are the engines for future discovery from biomedical data. I'd like to thank everyone who has worked on all of these different projects, as well as all the funding that we have received to do some of this work. Thank you so much.
Thank you. Thank you, Mahmoud. Thank you, Faisal. So welcome. We are here connected. So it was an incredible presentation. I have many questions because I think it is one of the most excellent work that we have ever seen with AI. So I will start from the podium, but don't forget that we have also people connected online. So if you have any question, please. Now is the moment. Okay, we have one question from Valdebron. Adria. No, Adria.
Thank you for great talk, and really amazing the job you are doing. It's super useful for the community. So I wanted to ask regarding you showed at the beginning that specifically for uni and cons, there are several studies out there that are already being used, those foundation models, to develop new biomarkers. But my feeling is we are still far from the clinic, at least in some cases, for example, when predicting genomic mutations from pathology. So I just wanted to know your thoughts about that. And if that's the case, what do we need, or what are we missing to validate those biomarkers so then we can reach the clinic?
Yeah, so I think predicting molecular alterations from histology, the key challenge has been around the performance. So for some, you can find a very clear morphologic signal that correlates with the molecular markers. In those cases, I think it's only a matter of time before these image-based biomarkers are used, but a lot of other cases, there is a morphologic signal there, but it's not strong enough that you get universal performance across patients and cases, and those are sort of unlikely to be used at this point. And there isn't a direct linear correlation between feature representation being richer and the performance improving for these what we often call as non-human identifiable phenotypes.
Okay, thank you. Any other question? So I have a question for you, Faisal. So I have many questions, but I will start with the first one. So the first one is, you showed in different slides, but especially in one, that obviously the multimodal representation, multimodal foundation models, you have demonstrated that are really efficient, also with very good performance related to some tasks, the diagnostic ones. Still, I can see you show that, for example, for prediction task, we are a bit obviously, right, a bit low as performance. My question is, when we have and we need to do fine-tuning, and so we need to add data sets with label data. I mean, do we have, I know that we don't have a size, but can you tell us how we can improve this part? Because this is essential for us. Because until now we are with the prediction, especially of immunotherapy or target therapies, we are really still at the level of narrow task or specific task. So how we can integrate together with the multimodal fashion part?
Yeah. So the goal of multimodal foundation models for us, the way we've been looking at it has been that how can you use complementary data across modalities to improve the image-based representation. The reason contrastive learning across multiple modalities has been so interesting for us is because only a fraction of data that we have is like truly multimodal, where we have all the other modalities, or from a machine learning point of view, all the other views corresponding a particular case. So if we can use those set of data for which you have all of this information and contrast across them and try to improve image-based representation, the hope is that the richer the image-based representation is, the fewer data points you would need when you pose your downstream classification problem for all of these tasks, including for treatment response prediction. Treatment response prediction is inherently a very difficult task because it's very difficult to get pre-treatment cases, in particular at locations where these kind of studies are running at tertiary cancer centers. So our hospital is a tertiary center, or the series of hospitals we work with, they're all tertiary centers, and we often don't have access to the very first biopsy or the very first instance of disease, and we often have to go back to the community center or the hospital where those procedures were done, and just by virtue of that, we just have very few samples which can be used for posing this kind of a problem. So all the examples that I showed around treatment response prediction have very few data points to begin with. But the goal of the rich representations, whether they come from unimodal or multimodal foundation models, is to have the ability to use fewer and fewer data points to get to useful performance, and we've come a long way. So I think if you look at the scale of data that we have reduced from back in 2019, where sort of the established standard was that if you were not using pixel level annotations, you needed about 10,000 slides in a multiple instance learning based setting to train a model that would reach equitable performance, unless you're dealing with larger sections where large portion of the tissue is correlated with disease detection or subtyping or some of these easier tasks, all the way to now where you could be using a few slides in a few shot setting and still get clinically useful performance for tasks that are really morphologically distinct, like detection, subtyping, and all of these other sort of easier tasks. And we've started to look into these more difficult tasks where even having under 100 data points, you can begin to get some useful performance. And for a lot of the treatment response tasks at this point, the performance is not clinically useful, but it is useful in terms of pointing to morphologic markers that might correlate with a response or resistance to treatment.
So I have another question because it's correlated with this, so thank you. The other point is not only the size of the data set that we have with patients, but the other point is the data modalities, right? Because when we go and we complex, for example, focusing in this case, I'm focusing now in immunotherapy and multimodality in lung cancer, for example. And if I imagine to use a multimodal foundation models, and I imagine, for example, 4 data modalities, which in this case, all right, it's digital pathology, real world data with lab exams, radiology and genomic, right? How much strict I have to be with my multimodal foundation models that I have to use to analyze and to fine tune my data? Do the original foundation models need to cover all the 4 data modalities? For example, I'm saying the use case just for the other to understand. Or let's say we still can use a foundation models which, for example, I don't know, it covers 3 of these 4 data modalities, but still can help us. Instead of and this is another more, it's a bit technical maybe, but instead of, for example, using single foundation model, extracting the features and then put in a more, let's say, narrow multimodal or deep learning, for example, using deep learning models from Opsora, for example, integrating them in a more late way or intermediate way.
Great. So it all depends on how you pose your problem, right? So if the goal is to just get richer image-based representations, you could use all of these modalities and contrast against them, and with the hope of getting richer image-based representation. And the consensus or the evidence, empirical evidence that we have so far is that you can get to equitable performance using fewer data points if you have multimodal data available. Now, once the model is developed, then in a downstream setting, you could just be using one of these modalities and extracting features from just that modality and posing that into a supervised problem. So the recommended workflow is that when you train your foundation model, you can use all the modalities that you have available in a contrastive setting, and you might have, your favorite pick for what you eventually want to use. And histology is a good one because it's universally available, it's increasingly digital, and maybe you just contrast against histology and lab tests because those are the two easiest modalities that would always be available. And it would use some features that exist in the lab values as complementary to histology to improve histology feature representation. And then downstream, you can just be using histology. The key behind this is that the diversity of data is much more important than the quantity of data, and this was established in the Dino V2 article from Meta, which really is sort of the foundational study that establishes a lot of principles in this area. And multimodal data is just much more diverse, and it relies on the redundancy across different modalities to enrich features of a single modality. In the past, what used to happen was that when we were fusing all of these modalities to do some kind of classification task or outcome prediction task, we needed to have all of these modalities available. But since now contrastive learning is common, you could make use of the essence of all of these modalities in your pre-training, but then not use them in your post-training step.
Okay, there are some other questions. I want to give the floor there. Okay, so we have Adria. He is Adria.
Thank you, Ursula. Thank you, Faisal. It's been a really interesting presentation. I will go fast with my question because I see there are a lot. We are definitely living a moment when this is exploding, and we have new foundation models for pathology every few days. And your group is truly following this up, which is really amazing. We have even this internal joke in our group of taking the chance of this Congress to kidnap you for a couple of months so that you stop. Because we are struggling to keep up with the path that this is taking. But yesterday, Jakob mentioned that obviously at some point this has to reach a plateau, and we will more or less have the foundation models that we need, and we will probably kind of slow down. Do you foresee when may this happen? Do you think this is something that it's close, or you still have like a lot of things to try in the pocket?
So this is a reverse research question. Okay, thank
yes,
you.
Yes, definitely.
Go.
So, so this is my opinion on this. The unimodal foundation models have already begun to saturate in performance. If you look at all of the frontier models that are available today, most of them have very similar performance. So I think our frontier model is the UNI2 model, which works at a patch level, and then we also have a slide level model, and we have more coming. But all of the frontier models at a patch level, if you look at their performance, there might be some statistical significance across it, and that might correlate with some kind of training distribution that could have been used. But in principle, they are all very, very similar in performance, and performance has largely saturated. This is akin to what we have seen in other areas, like for real world images, that after a certain point, adding more data does not necessarily improve performance. And pathology is a more specific domain, and the amount of diversity you can have there is limited in comparison to what you can have in real world images. So that aspect has saturated, or is beginning to saturate. But what I do believe is that the multimodal foundation model aspect would continue at least for a while, until we also saturate these models that would give eventually patient-level representations, representing all of these modalities combined together to give a single representation about the patient. So that's my view on this. Where things could go out of model, or the scaling laws might be disrupted, is in events where we might have algorithmic breakthroughs, right? So we have seen prior algorithmic breakthroughs lead to just a tremendous improvement in performance. I guess Dino V2 was one of them, and before that, or just around the same time, CLIP and COCA, like the two multimodal contrastive frameworks, also led to a lot of growth. So I can anticipate where a drastically better algorithmic approach in training some of these self-supervised models would lead to substantial improvement in performance for unimodal representations. But my belief is that multimodal representation learning would sort of continue and would sort of dominate this year and part of next year until we get to some kind of saturation performance for those models as well.
We have another question there. Okay, so.
Hi Faisal, my name is Bill, part of the Crispin Lab in Cambridge. Just reflecting on the talk you've given today, you did 3 foundation models, Uni, Conch, and Threads. You've kind of got different modalities with which to contrast. You've got the images themselves, and in Conch you've got the text, and in Threads you've got the transcriptomics. And in general, your point, I think, was that the more kind of orthogonal multimodal data, the more improved pre-training is. I was just wondering, with regards to a specific modality, say if you had to choose one to contrast your imaging data to most improve the image representation space generated by your foundation model, what's your intuition on what makes a good contrasting modality? Why transcriptomics is better than text, for example? Thank you.
Yeah. So it's a really good question, very relevant. So when we contrast against modalities, if you look back at what is the fundamental machine learning concept that we're using, we're essentially saying that we have multi-view data, and pairs of data have a certain amount of similarity, and everything else outside of that pair is effectively dissimilar. And you use that concept to reinforce similarity across modalities that we know are paired, and differences across modalities that we know that are not paired. And what happens is that it exploits the redundancy, similar features that might exist across similar modalities, similar aspects within those modalities, to reinforce signals for each individual modality. So in light of that, if you think about text is inherently very subjective because it's written by humans, and we're making an assumption that there would be similar text written by humans across cases, and and that's just not the case. And if you're contrasting against, for example, pathology reports, depending on who the pathologist is, it could just be the diagnosis or a morphologic description followed by diagnosis. So there's limited consistency there, and contrastive learning does not like inconsistency. So in light of that, transcriptomics is a very good second view, because we hope that, as long as the lab is sort of well calibrated, we are going to produce pretty similar results for transcriptomics across similar patients. This is why the sort of toy example article that we did before Threads, just by using the TCGA, was such a big indication to us that we should scale by contrasting with molecular data, transcriptomic or otherwise, because it's a much more objective second view of the modality versus using text information.
Really boosting the whole world around these topics. So thank you. I have two. I would like to have your comments about two, let's say, hot topics. One is about ethics, biases, and accountability. And the second is, we were commenting before about the use of AI-based tools, especially when moving to treatment selection, where the results are less strong, move from giving an overall success rate to distinguish between patients where the prediction is sure, it's highly probable, so the certainty is high, to patients where the prediction is more uncertain and further confirmations are needed. Thank you.
Yeah. Thanks. They're both very important points. So, ethics and bias. There are two aspects to this. The first aspect is that there is an ethical dimension to everything that is being done in machine learning today, because our scaling laws have changed so much. So, if we go back just a few years, we were often looking at very specific problems, and our ethical approvals and IRBs reflected that. So we used to get IRBs corresponding individual singular projects that, well, we want to study, disease X, Y, and Z, and we want to build a supervised problem around it. The scaling laws have now changed. Instead of just being, adding more data to your training, as we used to do in a supervised setting, today there are three scaling laws. We can scale at the level of pre-training, we can scale at the level of post-training, or now we also have test time scaling. So many different ways to scale your model and improve performance, and that has led to it's an ethical crisis, because we want to get approval to be able to use as much data as possible to pre-train these models, and this effectively cannot happen without IRB or whatever ethical infrastructure we deal with, without them improving some kind of an exception on using data from all patients, whether they were consented or not, in in a setting where we are using these cases as access human material post diagnosis or post treatment or after the patient has already left the hospital. There are many teaching hospitals, including where I work, where they consent all patients, and everyone is by default consented unless they essentially opt out, and there's a different ethics dimension to that question too. So the ethics of developing these AI models in a situation where some patients may have consented to their data being used for research while others may not have, and you could get an exception to that through your institutional ethical approval is still an open question and actively being debated. Your other point around biases, so we actively investigate biases across all protected subgroups in the models that we developed, and this could be against, I mean, in the US this is often categorizing patients who have insurance and who don't have insurance, because there is a clear difference between when they get diagnosed, or income zip codes, or other socioeconomic disparities, and there is correlation between how these models perform. And all of these protected subgroups, we did a study last year, it was in Nature Medicine, and we tried to investigate this exact aspect, although it was corresponding a lot of supervised models. But the conclusion was that as your feature representations get richer, you can mitigate some of these biases, because they often come from reasons that have nothing to do with the actual protected subgroups. An example would be that if they're patients with socioeconomic disparities, or patients who don't have insurance in your training, in your assessment set, but there are not enough advanced cases in your training set, you might see a clear disparity in performance almost immediately. So, and then we also found that using richer feature representations really leads to a reduction in these biases, and we assessed all the modeling choices you can make to have a reduction in these biases as well. So this is something that we are continuing to investigate. Your other point and question is also really important around treatment response selections and situations where machine learning model performance is not very strong, yet the model can still somehow be useful. So we think about this quite a lot, and uncertainty is, as you mentioned, is really, really important for this. So a treatment response classifier that can classify patients for immune checkpoint inhibitor therapy in which that's about 70, 75, or 80% accurate, cannot be directly clinically deployed because it does not have enough of an efficacy at least from a machine learning point of view, to be useful. However, if you establish that the model is predominantly accurate when it's very certain, so you can get certainty and uncertainty scores from the model. Sometimes these are directly attributed to things like probability or other aspects, depending on how the model is structured. Sometimes you could deliberately estimate what the uncertainty of the model is, and if you establish that the model is predominantly, or in the majority of times the model is correct, if the uncertainty crosses a certain threshold, you can still use a model that might not overall be very accurate, at least to give you an indication for which patients are more likely to respond to treatment, and then you can use that sort of likelihood and take that into account, taking into account all other aspects of the patient, rather than having a binary model that just goes ahead and makes that decision. The other thing you could do, that if you have a model for treatment selection or other difficult models that don't perform as well, you could just use them as discovery engines. So you have a model that's about 80% accurate. Maybe you can go back and look at what morphologic features were used in making some of those treatment response determinations, and that could lead to the discovery of a potential marker that could then be independently validated.
Thank you, Mahmoud. Faisal, sorry. Can you give us, let's say that we are full here there are a lot of junior, let's say, doctors, but also computer science. It's a mixture of students and future AI experts and AI experts actually. So give us, I don't know, one message. I have went through your recent publication on views on Nature and was very nice, and I was also showing in different congresses. So, because I think that we need a take-home message, because here is also an AI for Oncology Congress, so based also on implementation, right? I was very fascinating around the 3D work that we are doing with the pathology, and also thinking for the next implementation, what we need to work more in terms also in terms of collaboration in order to make it happen and to implement whatever you are producing. So I thank you again, as Alexandra did, for your open source tools, because we are not there, unfortunately, with the radiology tools, foundation models. We still need the Google foundation model and CT scan that we are missing, we cannot use, because, I mean, it's not released, so this is a great message. So give us a main message before we go to lunch.
Yeah. So,
and you for breakfast.
my message is, and I think I wrote that in the Nature message comment, is that we need to focus a lot more on benchmarking and validation and establishing how well these models work. Right now, the reality is that the field is moving so fast, but unlike a lot of other communities like computer vision or natural language processing, we don't have well-established benchmarks for model comparison. And in a field like computer science, where they inherently rely on benchmarks, they're really used to just naturally agreeing on benchmarks. So once these benchmarks are established, everybody uses them. People use consistency in pre-processing and post-processing steps. But what I often observe is that as the field sort of evolves so fast, there isn't a lot of consistency across our benchmarking in biomedicine, and maybe it's made complex by the fact that some foundation models are trained on public data, some are trained on internal and private data, and then assessed on public data. So maybe consistency is really difficult to establish in the first place. But we need really good, consistent benchmarks, because it's very important to assess and analyze how much improvement you get going from one model to another. And the reason is that these models are incredibly expensive. They're expensive in terms of data collection, data generation. In some areas of biology where specific new data is being generated to develop some of these foundation models, it's very, very expensive to collect this data. But they're also very expensive in terms of training. They require a lot of electricity. There's an environmental impact and factor to it. So how many models you need to train corresponding a single modality is also up for debate and an open question. Do you really need 50 different groups to be working on all of these foundation models? Is also kind of open, right? So once they saturate, the bigger focus should be on downstream tasks. But to do all of that, there has to be better benchmarking of these models. And unless we establish these benchmarks today, we're at the risk of just spending more and more resource in developing these models without having a clear sense of what is working for us and what is not working. It is very common, even among some of the frontier models, that every single group developing these, and this is not by intention, and this is not their fault, they're using benchmarks that are just inherently curated for themselves, whether from public data or from private data. So I think benchmarking is perhaps the biggest risk that we face in terms of future uncertainty for what would happen, and we really need to work on developing standardized benchmarks as we go into more and more complex models that incorporate more and more data.
Thank you. I totally agree. Even now that we are coming with multimodal foundation models, which data set the benchmarkings probably are very few compared to the unimodal one. So now in front of everyone, I am directly inviting you in the next meeting. We have the save the date, 7-8 May in Milan next year. It changed because will be this fourth edition, but also the first annual meeting of the European Society of AI in Cancer Research that with a group of friends that you know, Jacob, Mireille, and all that, we have founded. So you are officially invited, so put in the agenda in presence. And I don't know if you can see, but today we also foresee, because I think you have done incredible work in this, and we had a prize and award here for you. And I'm going to read this award for you now. I will bring to you, or probably will come here, we will see. So I am happy to award to Professor Faisal Mahmood in recognition of his exceptional contribution to advancing AI application in cancer research and his leadership in computational pathology, foundation models, and generative AI copilots for innovative diagnostics and treatment pathways. Okay, thank you very much, Mahmood. Thank you.
Thank you. Thank you so much.
We are doing a virtual picture, but you don't. Okay, so thank you very much, and we'll leave you free to go for breakfast, and we are free for lunch. See you at 13:20. Thank you.
Thank you. Thank you so much. Thank you.
Va bene.
Yes, I can hear you.
Good morning, Ms. Can you hear?
Yes, I can hear you. Can you
Okay,
hear me?
perfect. And we listen you so well. So, what did you think? We leave your presentation.
Afternoon session. Welcome back. The session is multimodal, and I first would like to introduce my co-chairs, Alessandra Pedotocchi from the Department of Bioengineering of Polytechnic of Milan, and Monica Ganzinelli from the Department of Medical Oncology, and Luca Agnelli, bioinformatician, Department of Advanced Diagnostics. And first of all, I would like to
So let's go multimodal. And to start with, of course, our first speaker is Saurabh Shah. He is leading computational cancer biology and chief of the computational oncology at MSK Cancer Center in New York City. Okay. Please, Saurabh.
All right, thank you so much. It's wonderful to be back at this now third edition of this meeting. I've had the privilege of being here for all 3 years, and it's really actually, I'm remarking on the growth of the field in just these 2 years since this meeting has started is really quite remarkable. What I thought I would do today, which has not really been mentioned too much at this meeting yet, is really focus in on what we can learn from single-cell biology in cancer. And let me see here. Okay, so I will be discussing. Maybe I try this. No. Okay, there we go. Okay, so I'll be discussing work that is carried out by these 6 people in the group. But I wanted to first frame the discussion by really remarking on the advances in technology that are now available to study tumors and to really learn and discover tumor biology. And this relates to single-cell techniques such as single-cell whole genome sequencing, where we can understand tumor phylogenetics at unprecedented resolution. Single-cell RNA-seq, where cellular phenotypes, state transitions, and cellular constituents of a tumor can be decomposed and analyzed at scale, so cellular phenotypes. Tumor immunology, where the interface of cancer cells with immune cells through TCR sequencing and single-cell TCR sequencing can now start to be related to the presence of neoantigens in cancer at single-cell resolution. And then finally, in the bottom left, spatial technologies, which will be the focus of today's talk. So all of these modalities, if you will, you can map these very nicely to, for example, the real-world data modalities such as pathology, radiology, genomics, et cetera. The same principle applies in that we're now starting to look at different molecular modes of tumors at single-cell resolution, and that presents an opportunity to integrate and learn all of these particular clinical endpoints that we care about: tumor evolution, drug resistance, new therapeutics, and in particular new classes of biomarkers for the new drugs that are emerging into the market. And a few papers in the bottom right there that illustrate this concept. So the audience doesn't need to be reminded that genome sequencing or clinical genome sequencing has really led to the numerous drug approvals and targeted therapy in many, many solid malignancies. However, as new protein-based or antibody-based therapies now are coming onto the market, we don't have companion diagnostics for the majority of these antibody-based therapies, one of which, for example, Alex rightly pointed out that there was approval of the TROP2 antibody drug conjugate, but for the vast majority, we don't have good tools. And so while precision oncology has been unlocked through genomics, the new wave of therapeutics that is really antibody-based does not have these types of same biomarkers. So this then elicits a major challenge, and I think it could be solved through spatial biology techniques. So the advent of spatial transcriptomics, multiplex immunofluorescence, which we heard about from Professor earlier today, has really changed the landscape of how we can study tumors in situ, and has created the Disneyland that we as scientists and pathologists can play in. And so some of the techniques that have been developed, such as imaging mass cytometry, codex, cyclic immunofluorescence for proteins, and then in spatial transcriptomics, Visium HD and Xenium, for example, are now really dominating the research world in understanding the landscapes of tumor biology in various different contexts. So here are some of the things that we can learn. So in spatial transcriptomics, the dimensionality of the data is that across millions of cells that may be present on a glass slide, we can measure the activity of thousands of transcripts at single cell or even subcellular resolution. Multiplex immunofluorescence, which is more protein measurements, we can start to now measure simultaneously hundreds of proteins, tens to hundreds of proteins across millions of cells. And so this really provides an image of a tumor as an ecosystem in one single measurement. And I think that's a very powerful concept. So we can start to think of the tumor as not only the cell intrinsic properties that are present in the tumor cells that are driving the cancer, but also how those cells behave in the context of their tumor microenvironment, including immunologic cells, stromal cells, et cetera. So this now elicits the concept of cellular architecture and crosstalk. What cells are interacting with each other, what are the receptor ligand type interactions that are driving that tumor biology, what are the spatial niches that are occupied by tumor cells, and that are what is the variation across that tumor, and how does that drive selection of tumor cells, the tumor immune interactions, how does the immune system actually control the tumor in different pockets of the tumor, and finally the spatial distribution of protein and gene expression may be variable even within tumor cells across a single glass slide. So all of this now invokes the concept of new classes of drugs that are antibody-based will require these spatial biomarkers to make sense of who will respond and who will not respond. So I'm going to step through now a few examples of multiplex immunofluorescence data. So this is a glioblastoma, and what you see here are beautiful representations of the expression of different proteins. This is a melanoma where the red cells are tumor cells, and you can very nicely see the infiltration of immune cells in yellow, the stromal structures in purple. This is a classical Hodgkin's lymphoma and another example of that. So what you can derive from these images is that there's incredible amount of information, content, and structure from being able to measure in a multiplex fashion the expression of multiple proteins in a tissue. And we can start to think about the biology at single cell resolution, but in situ, without having damaged the tissue, so we can put the cells in context of their neighbors. So this then leads to a computational challenge. So how do we move beyond these pretty pictures, which we all enjoy going to Disneyland and looking at, but we need a computational framework to encode the information that's present in these pictures. So we can think of tissue as a composition of interacting cells. And this spatial data is actually naturally encoded with something we call cell graphs. So in computer science speak, a graph is composed of nodes and edges. Here, the nodes then represent cells, and the edges represent interactions between those cells. It's a very natural representation, and that's been well trodden in the computer science literature, social networks, document clustering, many applications of graph-based architecture. So we thought we could just lift over those types of architectures onto this problem. And the major advantage here is that we get a much richer representation than, for example, convolution neural network, grid-based image processing type representations. And the output of applying these types of models is that we actually can start to derive biological and mechanistic interpretation of the output. So we developed this platform called Graffiti, and it's a cell graph encoding of spatial biology. And here, schematically, what we show on the left is a graph-based representation of the cells in a tissue. So we can identify the cells, those become the nodes, and then we can start to encode edges between cells as a function of distance or some other co-expression. And we can use graph attention networks that to create a cellular embedding of this data, and then a decoding step that can reconstruct both the cellular features and the topology of the tissue. So there are two major concepts here that we're trying to model. One is, what is the phenotype of a cell? And second, what is the topology of the cells interacting with each other? And we can do this simultaneously in this really nice graph-based framework. So here's just another way of looking at this. And so we use a multi-head graph attention layer that both encodes the expression vector of the cell, the cellular features, and the adjacency matrix that's shown there on the bottom. And so we can produce a latent space embedding of this data. That's the Z column over there. And then using a combined loss function, then we can reconstruct both the features and the graph. So the encoder part is uses a message passing algorithm that's been actually published originally in 2018 from Yoshua Bengio's group in Montreal, and is really a kind of a standard now approach of using multiple ways of encoding the information content from neighbors in the graph. And so then there's a multi-head attention weights, and that can be integrated together into a single continuous value shown there on the right. So that's how we encode the neighborhood. And then the dual decoder uses a two-term loss function that, first of all, minimizes the mean squared error on the gene expression from the decoded versus the observed, and then a binary cross entropy on the adjacency matrix. So these two terms are actually quite useful because they are weighted by this alpha and beta terms, and that allows us to actually put more weight on the gene expression information, for example, or more weight on the adjacency matrix. So you can imagine that in some cases where you have a very rich spatial transcriptomics representation, where you may have, let's say, 10,000 genes measured, that may be, it may be make more sense to put more weight on the alpha, whereas in a lower dimensional space, let's say in H&E or in a lower plex, multiplex immunofluorescence, you may want to put more weight on the topology. So the framework allows automatic learning of this, and I think can be, is quite flexible from that perspective. So then the last component here is the concept of cellular motifs, and this idea is that there will be cells or neighborhoods of cells that are shared across the tissue sample, and these represent distinct biological units that ultimately compose the total ecosystem of the tumor. And these can be shared across different parts of the slide or even between different tumors. So we can learn something, for example, of like B cell aggregates is a really good example of a type of cellular motif that is shared, and it has a very important biological function in stimulating immune response in tumors. And so this is done through clustering on the embedding and using a deep embedding clustering framework that's was originally published in this 2016 paper. We're not doing anything special here except using that exact framework. And what this does is allows us to create initial proposal distribution, and then we can refine that distribution with essentially like a k-means type of clustering on the embedding space. So then from the embedding space, we learn the decoder weights, and then from the decoder weights we can use this clustering. So it's a really kind of a nice iterative and joint inference framework for learning about the structure that's present in this type of data. Okay, so the major challenge in this field, and this has come up I think in Faisal's talk, is that we lack benchmarks. We lack ground truth to evaluate these types of approaches. How do we know that we're actually doing better than some other approach? And there are many, there are literally a dozen type of graph-based approaches that have been published in this field. And so what we set out to do is also to generate a synthetic data set and actually create a synthetic data generator that's parameterized and tries to represent some of the key features that we observe in real data. So what's shown here is 6 types of parameters that were used to simulate this data set. cell type, the degree of immune infiltration, B cell aggregates as a defined biological entity shown up here, and then also where we are in terms of parts of the tumor representing the stroma, the tumor-stroma boundary, and the tumor itself. And as you move away from the tumor-stromal boundary, we've seen, of course, that the expression vectors of the tumor cells actually change. They become more hypoxic, or they become different from the invasive front. So we wanted to try to model this as well, and that's what's shown here with these kind of rainbow layers of tumor cells on the bottom right. Okay, so then when we fit the model, we see very nicely that essentially this, without doing anything special to the model, we can really reconstruct these features that are present in the simulated data. And this has a couple of key ideas. So one is that the phenotypes of the B cell aggregates are different than B cells that are dispersed throughout the tumor. You can see the rainbow layers of the tumor cells, so the model can capture variation within cell type that are linked by topology. And the same thing exists for T cells. T cells that are embedded in the tumor are different than those that are dispersed throughout the stroma. Okay, so this is nice. This gives us a really nice confidence that the model is doing what we expect it to do. How does it work in practice? We'll show you just one use case example from this melanoma. This was a clinical trial, phase 1 clinical trial of intralesional IL-12 injection. And we had basically a small number of patients, but they really split quite cleanly into responders and non-responders. So my former graduate student, Miriam Pourmalecki, she spent years working on basically manually analyzing this data through painstaking combinations of protein expression to identify cell phenotypes. And then she's been working on this model along with Nick Seglia and others, and apply this model to this data, and basically without doing any modification, she can recapitulate her findings in the study, whereby we see this is the representation of the embedding space of these cellular phenotypes, and then what's on the bottom left is shown the source of whether these cells come from a responder or a non-responder. And you can see that these motifs that we find in the embedding space, they're actually highly enriched in either the non-responder or the complete responder. And so we have this really nice notion of that these spatial biomarkers or spatial motifs can actually are strongly associated with the response to this particular type of therapy. And so that's basically something that took Miriam maybe 3.5 years to do. We could actually reproduce with this framework just in a day. So that was really quite gratifying. We've now done this on several different projects. And I think it paves the way for progress in this area. So in the last few minutes, I just wanted to show just where we think this is going. So what we've done recently is look at co-registered MPIF data with the view that we wanted to understand whether we could find tumors that are likely to respond to TROP2 antibody-drug conjugates or TDXD, trastuzumab-based antibody-drug conjugates in the metastatic breast cancer setting. And so what we did is an MPIF on the data, and then in the next slice, we generated a Visium HD analysis. And we ran graffiti on this, and the takeaway from here is that there are pockets of the tumor that are expressing the target of the drug, but it's heterogeneous across the tumor, so we know that not all cells are likely to respond to the drug. So that's one takeaway. The second takeaway is that the transcriptomic layer provides this potential discovery opportunity. So the MPIF layer is very likely to be implemented in clinical practice, but if we simultaneously generate the transcriptome, we can start to learn the pathways that may actually be underlying the expression of those proteins and how they distribute in space. So then lastly, I wanted to just mention that In the single cell space, there are really hundreds of studies that are now being published in cancer, and the single cell RNA-seq data is being deposited in public repositories. The unpublished studies within MSK are also starting to number in the dozens. And so we literally have millions and millions of cells that have been sequenced from primary tumors with single-cell RNA-seq data. So what we've been trying to do is, similar to the developmental biology communities that have built cell foundation models for normal human tissues, we're trying to do this for cancer now. And we think that this is a nice way to actually help interpret the spatial transcriptomic data, because you could learn these embeddings and then project that data into the spatial data to better annotate and better interpret the spatial transcriptomics data. So this is where the multimodal integration, I think, comes in. All right, so in the last few moments then, I'll just say that spatial biology in cancer really is a critical new research frontier. Key thing is it extends well beyond current real-world data that just cannot capture the molecular states or cellular structures that are present in these tumors. The graph-based AI models are really a natural representation of spatial data, and we can capitalize on decades of research in fitting these models and more recent advances in the graph neural network space. The joint inference of expression topology and global clusters is really an effective way of encoding the spatial data, so we get the decomposition of spatial niches and distinguishing phenotypic differences within cell types. So, and then lastly, I think the spatial tools will absolutely be required to appropriately stratify patients onto antibody-based therapies. So in addition to it being an incredible rich discovery tool, I think this is actually going to be critical for understanding which patients should be stratified onto which antibody-based therapies. And then the final, maybe give me 10 more seconds, if you don't mind. I just wanted to mention, I've mentioned this to a few of you, I've recently become part of something called the Cancer AI Alliance, which I think will become relevant to some of the discussions we've been having. This alliance is supported by technology companies in a partnership between 4 major cancer centers in the US, and we're trying to build a privacy-preserving federated learning platform for sharing models without data having to leave, as we heard about in the first day. And so this is just getting going, but it's been heavily resourced by technology companies, and we're really excited about where this can go. And I just wanted to just mention that this is happening, and that maybe in 1 or 2 years we can expand to the global community. All right, so I'll stop there. There's so many people to thank that I work with, and they're all listed here, and especially thank the patients and families for participating in research. Thank you very much.
Thank you very much, Saurabh, and let me call Arcela to come, and don't go away. We have a special award for you as one of the first supporter of this conference.
Yeah. So hopefully this award tradition will continue. But yeah, after I wanted to, let's say, award some of people that, as you see, Jakob, Faisal, you're a lot of friends here that are working a lot. But I wanted also to thank you for your, let's say, staying behind us from the beginning in this thing. And I think that not only you, but also your team, Francisco, Kevin, everyone. So thank you for believing, because yesterday I mentioned the society, which is a European society. However, I didn't mention that we have the special advisory board, which would be all you friends that are here. I mean, because obviously one of the aim is to put everything together one day. So I wanted to award today Professor Saurabh Shah in recognition of his exceptional contribution to advancing AI application in cancer research, but especially the pioneer for multimodal data integration. Thank you very much. So my lab is here, And Kevin, Bohem, and Van Guri are like cited in my lab in every pipeline, and benchmark for everything. And obviously, thank you very much.
I think the credit really is to you. You're doing something very special here, and it's very evident from everyone that you talk to how much this conference means to them, and congratulations to you. So, thank you. Yeah.
Go back to work. Great pleasure to introduce you Dr. Mireia Crispin-Ortuzar. She is an assistant professor and group leader in the Department of Oncology at the University of Cambridge. Okay. Okay. Dr. Mireia Crispin-Ortuzar. She's an assistant professor and group leader at the Department of Oncology at the University of Cambridge, and a leading figure is in computational oncology. As you see, she is connecting from home, and she has the best ever reason for connecting from home. A baby is waited in 2 weeks, and actually, let's congratulate her.
Thank you.
I actually asked her to mention this publicly just because I think it's an important message to our young ladies around. I mean, maternity is something that is part of life. It's a great part of life, and it's never to be conceived as an obstacle for your career. And I think Mireia is a testimonial for that. Please.
Thank you very much. I hope you can hear me okay.
Yes?
Yeah?
Absolutely.
So first of all, I'm really sorry I'm not there. This conference is probably one of my absolutely favorite ones. Some of my favorite people, and just to see how this community is growing, the work that Arcella and the rest of the team are doing, it's just so inspiring. So thank you so much for inviting me once again. I'm sorry I can't be there, but I'll do my best remotely. So I'm going to start sharing my screen, so just give me 1 second. Okay. Right. I've made this full screen. Hopefully you can see it. If not, just let me know. So the title of my talk today is AI-driven multi-omic science for predictive cancer therapy. I'm going to try and do my best of giving an overview that hopefully will complement what Saurabh was talking about, and I'm going to focus on more, let's say, standard of care data and how we can derive models that can help us predict how patients will respond to therapy. I have a couple of disclaimers, and my first one is the usual more boring disclosure information. The second one is, even though I'm not there, I've sent three amazing members of my team, Hanya, Bill, and Zoyu. So please find them and ask them questions. They'll be able to give you even better answers. Please do engage with them. The three of them are absolutely wonderful. So why are we talking about data integration? I've been giving talks on this topic for a few years now, and I used to always start with this description of what we mean by data integration, and I think it's still relevant to some extent. So if we think about three typical types of data that we want to integrate: radiology, genomics, and digital pathology, the first question is data aggregation. How do we physically, quote unquote, bring the data together? And this is basically health informatics, IT challenges. And this is not to be underestimated. There's a lot of people working on this, and it's a really, really critical challenge. The second one is data fusion, let's say. How can we combine data to make better predictions? So they, all for one, one for all. So combining the power of the different data sources in a way that we wouldn't be able to do if we had only one data source. And finally, we've got data translation. What do the different data modalities tell us about each other? And this is more about biology, about explainability, about understanding what is behind some of the biomarkers that we sometimes use. Now, this is a little AI doctor that's going to help me in the talk. And the question here is, does this classification still hold nowadays? And I'm going to discuss that in the second part of my talk. So we'll discuss it later, but just keep it in mind. I think for now, this classification is still useful. And what I'm going to argue today is that the reason most of us do data integration is essentially this situation that we've got here. This is a multidisciplinary tumor board meeting in which clinicians are trying to essentially do data integration as their main job. And this is what's happening every day in hospitals around the world in very, very similar meetings. And so these meetings work, right? I mean, this is the reason that we do them. So we know already that we can integrate data and that there's patient benefit in doing it. So an obvious question is, can we do that systematically using computational models? But even more importantly, the way oncology and healthcare and, well, basically, the world of data as a whole is moving, the amount of data that we have to process is only going to grow. And we're talking about omics. I personally come from the imaging side of things, so medical imaging, and more pathology as well. But we're going to be having to integrate data from patients' wearables and environmental information, etc. And this is right. This is the way in which things should be changing. But it means that it becomes really, really important to have very powerful ways to integrate the data systematically and make good predictions. So what I wanted to do next was to give you a couple of examples, 3 examples in particular, of how we've derived predictive models for treatment response prediction in the last couple of years in 3 completely different examples. So I'll start with the oldest one, which is a prediction of breast cancer treatment response. And here we looked at early and locally advanced breast cancer patients who were receiving neoadjuvant therapy and then went into surgery. And the reason that this was a very interesting question is that even though this is a pretty typical approach, there's a whole spectrum of response. You have patients who will get pathological complete response, the tumor is gone after the therapy, and you have a whole range of residual disease types of responses all the way to RCB3. And so being able to predict who's going to end up in each category can be, would be really, really useful. And the question that we had was, how could we make this prediction at diagnosis? And so we used data from a trial in which the patients received multi-omic profiling, including whole exome sequencing, shallow whole genome sequencing, RNA-seq. We did also digital pathology, so quantification on H&E, and actually there were also some radiology variables, mostly focused on volume of disease. And so we took this and fed it into a classical machine learning approach, and this is going to be a theme of my talk. A lot of these models have traditionally used these types of classical approaches, but we did it in a way that was very robust, very strict, and just based on the features that we were interested in. And I mean, if you look at the sizes of the data sets, it's 147 for training, 75 for testing. They were not very big, so it made sense to start with this. And what we found is that actually we were able to reach very, very high predictive power, particularly as we started integrating more and more data. You can see that really nicely on the left in that plot that shows AUC as a function of the different data sources that you integrate. So in the end, we got around 0.9 of AUC. But one of the messages that I really like about this this study is that if you look at on the right-hand side, you can see the feature importance for the final model. And you see that there's a dark blue feature at the bottom that's lymphocyte density. This is effectively lymphocytic density estimated from H&E slides. So we used a computational pathology method to identify lymphocytes, quantify the density, and then use that as a marker. And you can see how even though we have a whole collection of features that came from the other data sources to evaluate immune activation, evasion, different processes. So what you would expect is a very rich evaluation of that immune activity. Actually, the model preferred the lymphocytic density from the H&E in terms of the importance of that model. So that really illustrates the value of doing the integration. And there's a similar story around HER2 status, ER status, and the RNA-seq equivalents. So we have ESR1 expression, ERBB2 expression. The model preferred the RNA versions of of these markers, which again, initially we thought wouldn't be the case. We thought, of course, it's going to be HER2 status because this is so well known. So it really showed why it's so useful to do this type of integrative kind of work. Moving on to a completely different kind of area, ovarian cancer. Those of you who know me know that it is a disease that I'm very, very interested in. It's highly heterogeneous. It's diagnosed when it's advanced. And so typically what we find is this type of metastatic presentation. And what you're seeing here is a CT scan of a patient where you can see all of the different lesions in the different colors. And so we decided to ask the same question here. How can we predict response for ovarian cancer patients to neoadjuvant therapy before they get surgery? And so in this case, and I hope you can see my cursor on this screen, what we focused on was the volume change during that neoadjuvant treatment. And we were able to do this because our radiologists spent a huge amount of time delineating the lesions for every single metastatic site. And then in terms of the features that we used for the prediction, we obviously had to include radiomics. And again, this is a traditional approach to this. So looking at the shape and the volume of the tumor, looking at the intensity, looking at the texture, and creating a whole collection of features from that. And then we integrated that with blood biomarkers, including CA125, which is very common for ovarian cancer patients, and circulating tumor DNA features. And for circulating tumor DNA, we actually had a very restricted kind of approach to it. It was I know that we could have exploited that more. For example, if we had looked at dynamics, because we know that that's likely to give us more predictive power. But we were trying to be, it was a proof of principle thing. How far can we go with integration at diagnosis if we don't look at longitudinal evolution or anything like that? And so the main message from this paper was that radiomics significantly improved response prediction when we looked at these categories of features. And this made sense for ovarian cancer and for the types of endpoints that we were interested in, because it was capturing a lot of that heterogeneity that we've seen in the disease. And what's nice is that we didn't only see it in terms of this volume prediction, which is what you see on the left-hand side. So this figure is showing you how the error in the prediction goes down as we add the radiomics. But we also saw it when we looked at how good our model was at classifying patients in terms of their RECIST response. So you can see that nice separation between response and stable disease in models that include the radiomics and the ctDNA. The final message, as you can see here, is that the ctDNA features didn't add much to the prediction, didn't make it worse, but it also didn't help. I know that this is not the end of the story, but it's interesting to see how powerful radiological features can be. And to me, that's another important message, because very often radiology is left out of the multi-omic kind of collections, but for some diseases, it can make a big difference. The third example I wanted to give you is one that's hot off the press. It was published just a couple of days ago. And here we looked at advanced kidney cancer. And I say rare because kidney is not as common as breast cancer, obviously. But also here we're looking at cancers that are advanced because they are growing into the vein. So they're growing into the renal vein and sometimes inferior vena cava. And these patients can have very complex outcomes. And so in the clinical trial that we looked at, they were also testing a drug, again, in the neoadjuvant setting. And so it made sense for us to say, okay, can we do the same exercise? But in this case, looking at the properties of the tumor and the thrombus, which is the name of this invading part of the tissue. And in this trial, we obtained radiological information. So we had MRIs. We also had blood-based biomarkers. We did flow cytometry and looked at a protein panel. And then we also had samples. So we were able to do image analysis and quantify things like vessels or different immune cells. And we also looked at RNA-seq, but we actually didn't include it in the model. We used it only for validation of the final conclusions. And again, using a classical machine learning approach, which we had to do because this was an even smaller trial. What was really striking, when we did it, I thought there's no way we're going to get something very, very predictive here. We checked and double checked and triple checked. We were really surprised to see that thanks to the sparsity of the model, which was something that we had enforced, we wanted it to be a really robust, really sparse model. We ended up with a highly predictive model. You can see on the left, the ROC curve for baseline only features in green, and then in orange when you add the dynamic features. So when you added some of the evolution of the block-based biomarkers, which reaches an IUC of 0.9 and above. You can also see that nice separation between responders and non-responders in terms of the likelihood that's being spat out by the model, and you can see how it improves as we add more features. And what's really beautiful is that actually this was driven by just a few immune and angiogenic features that you're seeing here on the right-hand side, some of them coming from the digital pathology, some of them were cytokines. And you can also see really clearly that interaction between them. And so you can see why we needed to do this kind of integrative approach in order to get the best response prediction. And so this was really, really exciting. And this now another clinical trial, the WIRE clinical trial that's ongoing, that's going to validate some of this. So I think one of the conclusions from this has to be that data integration can be highly effective with classical machine learning approaches. And we've seen this over the past few years. But clearly, this is not what the crowds are chanting. What the crowds are shouting is that we are now in the language era, in the era of foundation models, and this is something that we need to be thinking about. So, what does all of this mean in this new era that we're in? So when we now talk about multimodality, this is from the Biomed Pass paper. Often what we're talking about is models that take in a whole variety of data types, in this case, lots of different imaging techniques, for example, and usually text, right? That's the language element. And a lot of the time, really, these are data translation types of tasks, as we were saying at the beginning, text understanding or summarization of captioning. I know it's not exactly translation, but basically you're going from one modality to the other. So it is translation from that point of view. And what's really interesting is that I would argue that we have this new type of multimodality that we're looking at as well. And this, I've stolen this from Faisal's beautiful paper from last year that presented Conch, in which what we're seeing is that by joining together two data modalities, in this case, the report, so the text and the images, you're getting a better representation of the data. So this, gave rise to Conch, which is an extremely powerful encoder for digital pathology. And so this would be data integration from the point of view of data enrichment, which I think is really, really interesting. Now, what we are interested in, obviously, is this, right? Ultimately, what we want is to help patients. And so we still want to go towards that final integration piece. But really, the reason why having language is so important and why these models are so important nowadays is that it's pretty much, it's staring at us in the face. Language is a universal integrator. And so all of these exercises that we've been seeing over the last 1 or 2 years naturally are going to lead to a new way of doing integration. And I've stolen this figure from one of Jakob's paper. And here, the main point of the paper was very practical. It was about how language was going to change the way in which healthcare is delivered logistically. But ultimately, if you think about these different modalities that you have here on the left, if you have a really good way to translate that into words, then it makes sense, to use that for integration. Now, obviously, there are challenges to this, and this is not the only way in which we can integrate data with the new generation of models. But the message here is that it's really important for us to be pushing these different kind of types of models that we're deriving individually so that we can achieve this ultimate vision of integrating in the clinic. And so just to wrap up my talk, I just wanted to give you a couple of examples of how we in our group are trying to push forward some of these models. And it's basically a teaser of some of the posters that are displayed outside. So the first question is, how can we bridge the scale gap? And this is something that for me, as someone who's very interested in radiology, is very, very important, because I want to be able to bring together the macroscopic description from radiology to, and the tissue description and the subcellular description all together. And so a common challenge that we see is that in computational pathology, often models will focus on patches, but really what we're interested in is whole slide images at the very least, if not the radiological scale. And so the poster that Zoyu has presented at the conference is presenting Alpaca, which is the first pan-cancer generic model that can look at whole slide images in the context of a visual large language model setup. So it's for question answering. And so Zoya has put together an amazing data set of questions and answers and derived the alpaca framework, hence the cute alpaca in the middle, because it's based on llama as an LLM. You also heard from Hanya about how we need to test the limits of LLMs in areas of cancer that are really important, for example, the early cancer journey. And this is also something that we as a team are very interested in. And in fact, if you think about early detection, the types of work that we need to do are sometimes very different. So the work that Bill has been doing has been around how we can detect kidney cancer early. And so the multimodality of the work that he does is trying to combine data types, in his case, imaging types, so contrast-enhanced CT scan and non-contrast enhanced CT scan, in order to get the best possible signal, but to deliver it to patients in the least harmful way so that you can develop a screening program around this. And he's got some really amazing results that are basically being translated now into clinical trials and further projects. The last thing I wanted to say is I haven't talked about agents. This is also an area that a lot of us are very excited about. But even if in the future this is all replaced by our new medical AI doctors like the one I have here on the screen, agents will still benefit from having access to these models. And this is very similar to what we've seen in the imaging field. We see the very powerful, very general, segment everything kind of models, but still some of the models that people have been training for years are the most powerful ones. And so having access to that previous work will still be very interesting and very important in terms of informing that new generation of models, and in the case of agents, literally running them probably. So that's my last slide, so I'm just going to stop here. And I just wanted to thank my team, and this is just a selection of the people who've contributed to a lot of the work included in here. And as I said earlier, very happy to take questions, but you can also ask the members of my team who are there at the conference. So thank you very much for listening.
Let me pass the word to my colleague Monica, and we will have a discussion after the next presentation, so if you can remain connected. Thank you.
Good morning. I'm pleased to introduce to you Dr. Jana Lipkova. She's an assistant professor in the Department of Pathology and Biomedical Engineering at the University of California, Irvine.
Thank you so much. Okay. Hey everyone, it's really great pleasure to be here and present. So I will speak about the multimodal data as everyone. And there are going to be two parts. The first focus on how we can use AI to integrate data from different modalities to improve. Oh, I'm sorry. Hello. So there are going to be two parts of the talk. The first focus on multimodal data fusion with the idea how we can integrate data from different modalities to improve outcome prediction in oncology. And the second part is about the multimodal data fusion, especially for the survival prediction. I'm sorry, the second is about multimodal foundational models. Okay, so I guess we don't really need these slides about why do we need multimodal data. Everyone here is very familiar with it, but it's especially important if you look at the cancer and especially survival predictions, because for instance, in brain cancer, histology and genomics are very useful, but still they cannot always explain the disparities in the patient outcomes. And there are a lot of macroscopic tumor representations like tumor volume, location, proximity of the vital nerves, even disruption of the blood-brain barrier in the brain. These are factors that basically impact patient treatment, surgery, radiotherapy, and everything. And as we saw beautifully in the previous presentation, the medical data are too complex to be integrated manually. It's like just too many different data sources, and how do you assess patient under the multimodal context? So we would like to have AI tools that allows us to integrate the data and build this uniform framework for survival outcome prediction that's going to be objective and analyze the different modalities. And if you would like to build your multimodal AI-based model, so this is my wish list of the features or properties I would like the model to have. Of course, we would like the model to be automated. We would like it to be annotation and segmentations free because not only segmentations are expensive, they can be very biased, especially for the survival predictions. It may be difficult to know what do you segment as predictive regions in the slide or in the radiology. I mean, of course, the tumor region is important, but what about tumor microenvironment? What about stroma? What about lymphocytes? So it's really hard to say what are the predictive tissue regions. So in other words, we would like AI models to be able to discover the predictive features on their own without having like insights from the human. We would like the model to be, we would like to have the framework that can be applied to many different disease models, so you don't have to train the same model for each cancer types you're looking at. We would like to generalize across different cancer types. And of course, we want it to be robust and generalize also to data from external cohorts. And a little bit of teaser for the second part, maybe we would like to generalize to other cancer types that the model didn't see during the training. So having more toward generalized AI. And of course, certain level of interpretability would be useful. So to address this problem, we designed CAMPORA, which stands for Cancer Multimodal Prognosis, Histology, and Radiology Framework, and CAMPORA is also 3. So that's why the logo. And the idea is we have one deep learning framework that's going to integrate data from radiology, histology, and genomics to make patient outcome predictions. In this case, we're going to be looking at the survival. And this is a weakly supervised model, so we don't use any annotations. The models are trained using patient survival as the only label. And to show that it's flexible, we apply the same model to the brain cancer and the lung cancer. So you can see there are like 4 different frameworks or 4 different models. We have radiology module, we have histology module, we have genomics module, and then we have the module that make the data integration. So for the radiology, the model takes as an input the raw CT scans. In the case of lung cancer, for the brain cancer, it takes as an input the 4 MRI scans that are used for the brain cancer. So we have T1, T2 FLAIR, and T1 gadolinium. For the histology, we take as an input the whole slide H&E images, all available H&E images for the patient. And for the genomics, any genomics data can be used, but in this case, we use only mutation and copy number variation. And I will go slowly, like briefly over the different sections of the model before we look at the data. So for the genomics, we use very simple approach. We just use self-normalizing neural network, which is basically, you can think about it as a deep neural network with some extra layers for normalization to allow to train more stable networks. The histology model, this is probably something all of you already saw. So we use multiple instance learning to handle histopathology data. And I will just walk very quickly about it. So we have to segment the tissue, we divide it into patches, we do the feature extraction using your favorite foundational models. Then you can do attention-based learning. Basically, you want to learn how to assign importance score to each patch based on how important it is for explaining the patient outcome. And then because we don't have patch level survival information, we only have patient level survival information, we have to make the attention-based pooling. So we're going to use weighted average. Basically, we weigh the features of specific patches by their importance, the attention scores, to build patient-level representation. And this patient-level representation can be then used to make survival predictions, or it can be used as an input for the multimodal model that we're going to look after. And of course, you can do interpretability by visualizing the attention scores. I guess you are probably bored by this part now. We did similar stuff for the radiology. Since in the brain cancer, we have 4 MRI scans, so what we did first as a pre-processing, we register all the brain scans to the same reference space, and we skull strip the brains for the data privacy. Then we played a similar game as with the histopathology, but instead of dividing the images into patches, we divide them in axial slices. And then we extract features from all axial slices. Then we concatenate the axial features. So we have like one axial slide level representation. We do a bit more concatenation, and we again do attention-based learning, where we train the model to assign importance to each axial slice based on how important it is for explaining the patient survival. So we don't have to segment the tumor, we just let the model to explore the different slices and understand which one is important for survival. And again, we do attention-based pooling, we make the predictions. And in the case of interpretability, now we will have like axial level representation. So we know which slide was most important for making the predictions. And in terms of data fusion, so there are many different strategies how you could fuse the data, and you may not know in advance which is the best configuration. So we implemented 3 different methods. We have early fusion, we have late fusion, and Kronecker product. So early fusion, you just concatenate all the modalities together, and you train single model that is looking at all the data at the same time. In the case of late fusion, you train separate model for each modality, like one for histology, one for genomics, and then you combine the predictions from the model to make the final determination. And Kronecker product it's type of early fusion, but you basically use Kronecker product to look at the interactions between different pairs of modalities to account for their relationships. So this is the design of the study that we did. We were looking at the lung cancer, including non-small lung cancers, and the brain cancer, and here you can see the data. So we collected all publicly available data that we could get hands on, and you can see the table shows the number of patients we have for the unimodal and multimodal data. And you can see, like, for the radiology, histology, we have like around 1,000 patients, but if you look at a subset of patients for which we have all three modalities, for the lung we have only 90 patients, for the brain we have like 200 patients with all three modalities. So this is like one of the challenges is multimodal data. How do you build large cohorts with the map all modalities for the same patient? And we also have the data from external cohorts that they have for the brain cancer. So we didn't want to like waste the patients. So what we did, we trained unimodal pre-training, unimodal model for each modality separately, and then we used using the patients that have only one or two modalities available. And we use this pressure subset of patients with all three modalities to do multimodal fine-tuning to learn which combination of modalities and their interactions are relevant for the patient outcome prediction. So we have unimodal pre-training, multimodal fine-tuning, so we can leverage more patients. Before I show you the results, I have one slide about the data fusion. So we said we don't know which fusion is best or which type of fusion is working in which scenario, so we explore all the different combinations. And what you can see here are is a performance score for the brain and lung cancer with all fusion methods across all the different combination of modalities. And one observation we saw that if you have fusion of histology and genomics, then the early fusion performed best for the brain and lung cancer, while if you have fusion of radiology and genomics, the late fusion was the best. And the impression we have from that is we can learn what we know from other domains like the image and vision, and we know that modalities that are highly correlated, they usually benefit from the early fusion because there is a lot of like correlation, and this unifying model can explore this correlation. Well, if you have data that are less correlated, then the late fusion is best because you can have separate models and then you just integrate the data. And I think this is what is happening here because histology and genomics are highly correlated. We can predict the mutations from the histopathology data, so that's why the early fusion probably was the most beneficial, while radiology and genomics are less correlated, so maybe the late fusion was the best. And for histology and radiology, the early and late fusion very, very comparable, while if you look at a fusion of all three modalities, then the late fusion was the best, probably because we have these different types of correlation of the data from between histology, genomics, and radiology, or because we have very small multimodal cohorts, so we don't know. So looking at the data, what we computed the performance of the model on the multimodal cohorts, and you can see the performance measured by the C-index and integrated AUC score, where each colorful column corresponds to one modality, going from the unimodal to multimodal. So the white column is all three modalities, and we trained the model on the glioma cohort in general, but then we also report performance for the low-grade and high-grade glioma separately, although we just train across all brain cancers at the same time. And we can see that for the GBM-LGG, which is the whole cohort, and the low-grade glioma, the multimodal fusion of all three modalities is outperforming the unimodal and bimodal models. While if it's the glioblastoma, the high-grade only, the multimodal model was only second best. And we have similar observation for the lung cancer, where again, fusion of all three modalities outperformed the unimodal and bimodal for the whole lung cancer cohort, which is the NCLC, and for the adenocarcinoma, while for the squamous cell carcinoma is actually fusion of pathology and histology that outperformed. So like a conclusion from this point can be maybe the fusion, it's not always the best because we have a small cohort, but in general, the AI can leverage complementary information in the data to make better predictions than the unimodal counterparts model. So this is why we want to actually do the multimodal data fusion. Now, the important question is, how do these models generalize? Because we know that generalization in AI is a really big issue, and we know that even unimodal models can drop in performance when you go from your local cohort to the external cohort. And if you have multimodal data, there is large variability across all the modalities, so this can definitely hurt your model performance. So we were looking at the generalization to the external cohort. And actually, we saw that the models generalize fantastically, or like very well. So here's the performance. We have data from the external cohort from Germany, and you have performance on the training data, which is the internal, and the German cohort is the second. These data, they came from clinical trial with very special inclusion criteria, and all the patients is almost the same genomic profile. They have the same mutations. So you can see that in the German cohort, the blue pile, which is the omics data, are performing very badly because, I mean, there is no distinction between the genomics data. But if you look at the integration of all three modalities, then again, the fusion helps to improve the performance significantly, and the performance on external cohort even actually outperformed the performance on internal cohort by 3%. So the models generalized really well to the external data, and we saw the same for the second cohort, which is from the US. We have only histology and genomics, but again, fusion of all three modalities outperformed the unimodal models, and we also have better performance on the training data, meaning that the models are able to generalize. And one of the reasons we think the generalization happened is it's because the models can leverage also complementary and redundant information in different modalities to suppress the levels of noise. So maybe that's one of the reasons why we generalize better to external cohorts. And of course, to know how the model perform in the clinical settings, so we compare the performance against standard models using standard genomic information. So we have tumor stage, patient age, gender. We have several common mutations, and we train Cox proportional model to see how our models perform against model based on the clinical biomarkers. So here in the purple is the clinical model versus in blue is the Campora, the multimodal, and we saw that the multimodal AI basically outperformed all clinical biomarkers for all cancer types and all the subtypes of the diseases. So there, it suggests that the model is able to learn some prognostic features on its own that are not part of the standard evaluation for the patient outcomes. And then we are all familiar with the interpretability, so you can use the attention heat maps to look what are the predictive tissue regions for histopathology, and we can look at the different regions for low risk versus high risk patients. This is probably something you saw many times. It's a little bit more interesting for the radiology, which maybe you didn't see. So what we saw here, we have the axial level importance, so we know which tissue slides were important for the predictions. And here you can see that we didn't have to segment the tumor, and the model was able to find slices that contain the tumor and consider them to be most prognostic. But then to refine the interpretability a little bit more, we computed GradCam and weighted it by the attention score, so we end up with the 3D representation and interpretability maps. And this is kind of interesting. So we look at all four modalities for the one patient, and we can see, so basically what is red was important for the prediction. And we can see like T1 gadolinium was much more important than T1 scan on its own for the glioblastoma patient. You can see that the model is really focusing on the tumor regions, even if it didn't have to segment it. And this is another patient with the low-grade glioma, so there is no T1 gadolinium enhanced, and the model is looking at the compressed ventricles, which is like secondary site of the tumor. And what is really exciting, if you look at the T2 scan at the bottom, because you cannot see my mouse, but normally your brain is like symmetric, and you have this so-called brain midline, which is separating your two hemispheres. And one of the prognostic factors for the brain cancer is actually the brain midline displacement. So it's like how much the tumor is shifting the one hemisphere to another one. And in the T2 scan, you can really see that the model is focusing highly on the brain midline displacement, even if it didn't tell it to look there. So it's interesting that it was able to find these prognostic factors on its own without having any insights from the human. And then we have interpretability for the genomics. So this is just for the completeness. We can look which genomic information was most important, how it does relate with better outcome versus the worst outcome. And of course, you can see that ADH1 mutation was really important for the predictions. Of course, you didn't need to train AI model and burn all the money to do that, but it's nice that the model was able to discover it on its own without having any insights from the human. So if we are looking maybe at the treatment response predictions where it may be not clear which genomic information is relevant, this approach can be something we can leverage. So this is the standard multimodal data fusion, and the second part is how we can use, is about the multimodal foundational models, which we already speak a lot today. So as Faisal basically mentioned for us in the image vision, the idea of multimodal fusion is to leverage data from different modalities to improve, to learn better feature encoders for the image representation. So like you can combine, typically you would combine image and text data through the contrastive learning, and you use the text information to learn better feature encoders for your imaging modality, so you can then use it and translate it for the downstream prediction task. And particularly in pathology, we have, at the moment, we have like two types of multimodal fusions. We have a combination of images and text, which are going to be models like PLIP, Cont, Chief, Titan, you name it, and we have Tangled as another type, which combine imaging and transcriptomics data. And we were very much interested how the foundational models, especially the multimodal foundational models, can be applied for the survival predictions. And this is nice segue to what Faisal was saying. So we also made the benchmarking of the foundational models with the questions for the survival prediction in oncology. So we were looking at 13 different cancer types from 4 different consortia, and we evaluated 10 different models. And this is going to be part of the study and framework we're going to be publishing soon, but there is very interesting twist for the multimodal foundations models I would like to speak about. So once you have these models, and if you want to test them and compare them, there are 2 things you can do. So of course you can do cancer-specific models. So you're going to train prognostic model for each cancer. So you're going to train one model for the brain cancer, and then you apply the model for the patients with brain cancer. And then you take another model that you train for the kidney cancer, and you apply it for the patient with kidney cancer. Like this is like your specific cancer-specific survival models. Another thing you can do is you can train generalist cancer model, meaning you take all the patients in your cohort with the lung, kidney, brain cancer, and you train single model across all cancer types. And then you apply the same model to patients during the inference that they have brain cancer, they have kidney cancer, you use the same model for all these patients. And the motivation here is, of course, cancers are very specific, and there are many differences and distinct features for each cancer subtypes, but there are also a subset of like common features that all the cancers share, like the famous paper called Hallmarks of Cancer by Hanahan. So there are some shared properties among the cancers that the model maybe can learn for. And this was like one of the motivations. Can we learn across the cancers to improve survival outcome prediction? And the very exciting part is once you have this model, you don't have to only apply it to the cancers that you use during the model training, but you can apply it to so-called out-of-distribution cancers. These are cancers your model never saw during the training. So it's like zero-shot survival predictions. Or like how you can think about it, how the survival features that you learn across cancers, how they generalize to new cancer types. So you can think about when you have rare diseases or new cancer subtypes. And this is the part I want to speak today because the multimodal fusion is going to play a big role. So we are looking at these out-of-distribution cases. We trained the model across 10 different cancer types, and we applied to 4 different cancers that were never part of the model training. So we have bladder, ovarian, prostate, and we have subset of rare lung cancer. So this is no non-small lung cancers. There are all the different lung cancer types that we could find. And here in the blue, you can see the performance from the ResNet 50 as our baseline. And you can see that the C-index is like usually less than 0.5. So usually ResNet 50 wouldn't be good foundational models. I mean, it's not surprising. Here is the performance with all the remaining 9 foundational models. And you can see that maybe this is not so impressive. This is zero-shot survival, but bear with me. We can draw a few conclusions. So what we see is that Conj model is actually the one that performs the best because it has C-index more than 0.5 across all 4 cancers that were never part of the model training. I'm not saying this is clinically relevant, but this is most consistent performance that we could see. And then this was followed by GigaPass and Titan, which are slide-level models. So what we can see here is that a combination of multimodal, like the Conj, which is images and the text, and slide-level representation as a Titan or GigaPass, has some potential for zero-shot survival learning. And there is another benefit with the slide-level models. You don't have to use multiple instance learning. You can also train like different types of model. You can have different loss functions. So we retrained the models using Cox loss and different batch size, and this would be the performance of the slide level embeddings models trained with the different loss across the patient cohort. And now you can see that the Titan with a different loss actually had really high performance across the cancers that were never part of the model training. So this is opening like new possibilities of like we can have prognostic models for the rare cancers where you have very small amount of samples, or we can start to think maybe about generalist cancer models gonna generalize for across the cancers that we never saw. Of course, these are like a first observation, but maybe you can use this as a beginning, and then you can refine for your for the rare cancer. Or like it's a very good starting point moving to the generalist model. And so with this, I will quickly summarize. So we were looking at two questions. One was the multimodal data fusion, and we saw that there is a benefit for the multimodal integration with the aim of improving accuracy and also robustness of the AI models. And in the terms of multimodal foundational models, we saw that multimodal foundational models can generalize across different cancers, including those that were not part in the model training. So we can start to think about like zero-shot survival predictions. And to conclude, like, of course, there are a lot of challenges with AI, especially with the multimodal AI, but there's a lot of potentials that we should leverage to help the clinicians and patients. And with this, I want to thank everyone and Arcela for inviting me, and all of you. Thank you.
Thank you, Jana. Please stay with us, and I invite also Sorab to reach us to the microphone, and I open the discussion to the floor. Yeah.
Two
There is
Alex
also
want
Mireia.
to make questions. Alexandra and Alex Pearson. Okay.
Thanks everyone for great talks. So my question, I was going to include Raquel as well from the previous talk, but so I'll ask to all here. Just because we can integrate all these modes of data, should we? The modes of data will require additional time, additional cost, and potentially delaying decision making on behalf of our patients. So should we demand our models tell us when it needs more data, for example, or include the actual cost of additional assays in the loss function? How do you guys think about this moving towards a future clinical practice state?
Well, I don't think we necessarily have to include all the data, and for some predictions or prognostic tests, not all modality is going to be relevant. Plus, you may also have redundancies across the data. So one thing you can think about it, you can use multimodal AI to find the relation between the modalities and figure out which modalities you don't need anymore. So this can be like a way to optimize your predictions framework. The other is through these foundational models. Maybe you can build once really big cohort to learn better representations for the imaging data, and then you just use this information to learn better representation and apply it only to images. So like transfer the information. Yeah.
I agree with all that. Just to add, I mean, that's what's already done, right? So the clinicians, you know better than me, but I mean, you synthesize information from different diagnostic modalities as it is. So if we can accelerate that process, then I think that's going to be advantageous. From a more scientific perspective, I think learning for example, genotype-phenotype relationships between genomics and histopathology or genomics and more multiplex immunofluorescence is going to be a real frontier for understanding how mutations in the genome manifest in tissue morphology or tissue architecture or even cellular phenotypes. And so from a mechanistic understanding perspective, we can actually use these models to generate hypotheses that can then be tested in the laboratory as well. So I think across the spectrum, the answer is yes, we should, because I think you can look at any kind of other field, financial modeling, climate modeling, all have benefited from multiple views of data or multi-sensor inputs that are integrated. So, the climate modelers now, are drawing from hundreds of sensors from the atmosphere or from on the surface of the planet, and are making really incredible inroads into that. So, I think it's a frontier area, and we in the cancer space, because we're generating this data in the provision of care, we absolutely should integrate because we're going to learn something. Yeah.
If I can add to that. Yes, I think you can hear
Please.
me.
Yes, please.
Just two very brief comments. One is about the data and the delays. I think that right now it's true that there would be a delay if we had to systematically generate every single source of data for every patient, but that doesn't mean that it's always going to be like this. I think it'll take us a while to get there, but I am confident that in the future we're going to have much better pipelines, much more digitally savvy hospitals that will be able to generate a lot of these data much more easily. And we've seen that already for histopathology, right? How trusts and hospitals are digitizing all the histopathology routinely, which wouldn't have happened just years ago. And the second thing I wanted to say is that a lot of the work that is ongoing in the multimodal field that would fall into the translation category that I was talking about, I think actually could serve a really important purpose for this as well, because if you can generate a biomarker that can behave very close to a genomic biomarker, but you can do it from H&E, and obviously Alex, you're the expert in this. then it'll be much quicker, much cheaper to get it. So this idea of generating poor man's models or poor man's versions, or simplified versions of the model that get you there in terms of the performance, but that are as simple and as cheap and as quick to elaborate as possible, I think absolutely has to be an objective of the multimodal model development that we work on as a community.
Yeah. So I have a question for Jana. So because I think this is one of the, when I do my, let's say, my two last slides every time, it's state of the art of AI and challenges in AI, but I finish always, and the same topic sometimes is in the both slides. So explainability is in the both slides in this case. But because, then I noticed that the slides are like predictive AI versus generative AI. So my question is how you are seeing all in this fantastic overview, thank you very much, that you did in the multimodal integration, also with the multimodal one, because we discussed also with Faisal some of the things today. How you see this explainability on multimodal can be, how you see it? Also in terms of techniques, no? All these data modalities, post hoc, ad hoc, Vanya has explained yesterday something.
Yeah, I think this is a really big question. One is for we have multimodal data and you try to understand not only which part of the slide is contributing to the prediction, but how does it relate with the genomic information? Like what is the multimodal interpretability, right? How the combination of features contribute. And at the moment, we don't really have good methods for doing that. And this is very difficult when we go for the translational medicine, new biomarkers. And even with multimodal foundational models, it starts to be your slide level embeddings, and we even lose the attention heat maps, right? So we are losing interpretability at the cost of better predictions. And it's something I keep thinking a lot about, but we don't really have good tools. Also for survival predictions, we have the attention heat maps, we know where the model is looking, but we don't know if it's increasing or decreasing. So actually I have a lot of questions I don't have answers, so I'm just adding to what you said. But it's very important if you want to think about translation, right? We need to get some insights. So I'm sorry.
Yeah. Maybe I can add to that. I think we're in the space of the field where we can identify forests, but we're not looking at the trees. So, for example, in histopathology, the unit of biology is the cell. And I haven't seen one talk here today that in this meeting that is thinking about cell, except for maybe my colleague over here. And I think this is the fundamental opportunity that we're all skipping over, is to try to model the cellular features of these data, because that's what's driving the biology, and I think that's where we'll learn something. So.
And especially if I can add what Julien said today related to these, we always also in our pipeline, we were dividing the gray area, which is especially for the prediction. I think that is exactly the area where the biology can help. And connecting with Alex, what he said related to the cost is exactly also related now to treatment prediction and survival. I think that we have passion that we can predict really easy, so not simple task, but simple patients to be predicted, which for sure there we don't need uncertainty, or at least the models are not uncertain to answer. And probably for there, the cost can be very low, because Scorpio done in MSK with, recently published with real world data and lab exams shows that there are simple models with MLs, with simple data, with real world data that can help us. And because in immunotherapy, we still don't forget, we don't have tools. We are just using our brain. So we don't have a benchmark. We don't have the genomic. So at the other hand, exactly when we need to, I'm trying to do some networking connections. So this is why uncertainty of the models are important for this gray area, because there we have to push the singles or the cell focus, then the biology focus, and there obviously for these difficult patients, which pass me the term, difficult prediction patients, we need absolutely to don't matter about the cost, at least in Italy, at least for until a bit. I don't know, because also we are in crash. So, but the message is that also we need to think beyond the tasks, also which are our patients, where to invest more and to rationalize more on that. And probably thinking about foundation models, just to multimodal foundation models, and which data modalities. I don't know how this, because it's not state of the art, right? And so I don't know how this will go. But what I imagine one day, which means that will not be for all the labs, is that we need a mother, the big Matryoshka foundation models, which try to cover some essential data modalities, and where when we ask to them the prediction for the survival, we can ask them with our patient with what we have, let's say, and essentially takes in consideration what you give us. I mean, probably, if this will go.
There is still a question from Raquel.
Yeah, I'll try to be concise. So first of all, thank you for the three excellent talks, and thank you, Saurabh, for sharing the newest data from your lab. This is, I think, one of the beauties of these small conferences in which you feel free to share the latest stuff, so thank you so much. I've got a couple of questions for Jana and Mireia. So Jana, you have nicely shown us that regarding multimodal fusion models, that if the data is complementary, probably late fusion is better, slightly better than early, while if there is more complementary information in the data sets, early is better. Mireia, do you have the same impression in your experience? And I'll also make the next question for Jana. How do you deal with missing data in the external validation? Thank you.
Yeah, so the question of whether late fusion is better is a really good one. I would say that I think early fusion has not been explored enough, probably. I mean, most of the work in this space has been focusing mostly on late fusion, but it's true that anecdotally what we're seeing is that it works better. But it might be because for radiology we don't have the best encoders yet, we don't have, we're not as developed as other areas like pathology, but it's certainly a really interesting observation.
Also, there is this idea of intermediate fusion, right, where you're trying to learn the features based on the multimodal context, which is what the foundational models are doing. So I think moving forward, it's going to be this mix of intermediate fusion and maybe some fine-tuning with maybe later early fusion. Coming to the question of missing data, this is something that keeps me awake. It's really difficult. Not only we have missing data in genomics, we have incomplete data. We don't have the same genomic profiles for all the patients. And actually, we are trying to develop some models for handling it, like using the attention mechanisms to shift the focus from the missing modality to the available modality. But at the moment, I have very mixed results. Maybe I will present the next time. But one way around, again, can be through the foundational models, because you can pre-train across the modalities, and maybe the encoders that you get gonna carry the information from the radiology. Maybe it's not satisfactory, especially from the radiology. I don't think we get that much information in the pathology. But having this, maybe with the light fusion, you can even handle the missing data, and we are trying, and I hope we're gonna get some better solution to handling it. But it's a really big question. So.
Maybe I'll just add one thing is putting my tumor evolution hat on. So multiple instance learning, I think, is incredibly lossy, because you're taking this depiction of millions of cells, which we know are heterogeneous in a tumor, and assigning one label to it. So, I would ask the question about whether we can start to have richer representations early in the embedding space that actually encode the heterogeneity that's in a tumor, and not ascribe a single label to the whole slide. That's going to be a much more potent predictor of targeted therapy, for example. So even if you have 2% of cells that look different and have certain properties that make those cells intrinsically resistant to the therapy, those are likely going to be the cells that grow out. And so none of this work is capturing the heterogeneity and tumor evolution properties that we know are driving these cancers to begin with. So I think we need to, and so late fusion, I think, is going to be very lossy, and so maybe we can start to encode that earlier in the integration.
So thank you to all the speakers. I would like to inform you that there are some small updates to the program, and so it's a very pleasure for me to introduce Dr. Francesco Trovò. He's an associate professor at the Department of Electronic Information and Bioengineering here at Polytechnic of Milan. It's your floor.
Thank you for the nice introduction. Thank you for inviting me here, Arsena. I will try to be brief because I know that we had really interesting discussion, and I think that, okay, it's a pity that Alex is leaving, but yeah, okay. No, you can go, no, absolutely, no problem, no issue. Today I want to describe a project we are developing about a multimodal implementation of a machine learning tool for treating or for predicting the treatment of immunotherapy in non-small cell lung cancer patient. So I would like to start from scratch. Okay, now I can start from scratch. Okay, so how are you deciding which kind of treatment you are giving to non-small cell lung cancer patient? Well, you have some guidelines from ESMO, which are getting more and more complex over time, but still these kind of guidelines are only looking at really limited amount of data. So here the doctors are only looking at ECOG and on PD-L1 marker. Probably we need to look at the patient at the 360 degrees, so we need to integrate more data. So we just had three incredible talk about multimodal integration. Why not to use that? Well, we are not yet at the level for which we can directly introduce this technique in the clinical practice, but there are some potentiality of this technique that can be used throughout the entire patient journey in non-small cell lung cancer treatment. In particular, if we want to look at just the treatment selection problem, we can identify a couple of hallmarks that can be treated with, that can be dealt by using a machine learning technique. And in the specific, we are, as this paper is mentioning, we are not yet at the level that for which we would like to use it in a clinical practice. So how we can get to this point? Well, we need to join forces at the European level, but even beyond. So this is a European-funded project called ITRILANG, in which we are using the synergy of different clinical centers and also technical centers throughout Europe and outside in order to generate a tool that can be used for giving interesting information to physicians and try to help their decision to make a more informed decision, I would say. So here we have some kind of a structure of the final outcome of this project, which is a platform which will be used both by patient, physician, and researcher for different purpose. I think that during this presentation we will focus more on the purpose of this platform related to the physician. So how it is structured? Well, as we already mentioned, we need data. Which data can we select? Well, first, data we already have, so the retrospective data coming from the center in the consortium, and this data clearly might be somehow not complete. So depending on at which point in time they have been collected, they might have different structures. So some patients might have only clinical data, some other can have also CT scan, digital pathology, and so on and so forth. But we plan also to collect some complete data. So in particular, another 2,000 data about just real-world data, while 200 data with some of the possible omic data that we can collect from patient, another 200 data with all the possible omics. Let's go a little bit into detail, but really quickly through the data that we want from patients. So first, when I'm talking about real-world data, I'm talking about clinical data, so tabular data, but also some behavioral data coming from, for instance, a wearable, and also radiomics and digital pathology images. But we will, let's say, complete the information given by this kind of data from blood level omics, tissue level omics, single cell, and stool. So also single cell, okay, I know you would have been really happy about this. So we started analyzing this data, and some of them has been already published at AACR annual meeting. We presented some study about single cell transcriptomics, but where do we place this data? We designed a completely independent platform, an independent platform that in the initial stage of the project will be used only for data storage and data imputation. But as you can see here, there will be many more functionalities that we will allow to be used by clinician, by researcher, and patient. These are the numbers updated to April, so we have roughly 2,500 data from retrospective patient, and we are currently enrolling more and more patients for the prospective part. How should the final decision tool that will be included in this project look like? So this is something really closely related to what we were discussing 5 minutes ago, because here we would like to have a tool for which, if we do not have enough information, we would ask for new information to the physician. So in a sense, we will start from gathering data which are in the clinical practice, and at the end, the tool will answer us either if we would like to give one treatment, a second treatment, so all the possible treatments that are available in the clinical practice, or I don't know. So if the tool is not sure enough about the answer, it will, let's say, stop the physician and ask for additional data. So here, depending on the uncertainty of the model and depending on the amount of information we think the model might get from additional source of data, the data will ask for these new sources. And then the third stage will be clearly to further personalize this kind of tool so that the model will introduce more and more modalities as they are required for improving the prediction capabilities. How it should look like, this tool. So it's the last button of this scheme. Well, a physician will have to insert all the clinical data. That will be really annoying, but it is required. Clearly, depending on which clinical data are the most useful, we can only ask for a subset of them. Then we will require also to give some images with some specific format and with some, let's say, pre-processing steps which are required. And finally, we can get a prediction. So it seems like I missed the only interesting part, which is the prediction. Why I'm not giving any number? Well, because right now it would be just a number, so either a probability or immunotherapy is working or not. This is not something that we can give to physician. We need also to give some more information. We need to introduce more let's say, a larger framework in order to give the right information to the physician. In particular, before it can be used in the clinical practice, we need to test and understand what's the clinical usability of this tool. And so in the project, we are in the process of doing a clinical usability study in which we will present some cases to the doctor and ask them to predict about the efficacy of immunotherapy, and then we will give also the prediction and some information about multimodal explainability of our tool, and we will try to understand if this might help, might significantly help or increase the prediction capability. But also, we should not look only at the overall survival of the patient or a primary outcome of the patient. We also need to look at other aspects of the patient life. First, the quality of life, of toxicity that the treatment might introduce, and also maybe the patient preferences about how the treatment might be given to him or her. And finally, but not lastly, the cost effectiveness of the treatment, because clearly we are in kind of a wealthy country, but we might have some constraint at some point about the cost of this kind of treatment, so we should also take into account this kind of matters. So let just me give you a couple of ideas on how to integrate this. So first, in order to integrate quality of life, you need to get feedback from the user, and so inside the project there is also an app which will give some information about how the patient is experiencing the treatment, while for the cost effectiveness there is an entire work package dedicated to the building of the cost effectiveness model that will be integrated in the cost function of the final predictive tool. Finally, clearly here we are somehow focusing on a specific kind of tumor, non-small cell lung cancer, and a couple of treatment, which is immunotherapy or immunotherapy plus chemotherapy. But clearly, this can be somehow extended to new diseases. Okay, if what the Dr. Iana was mentioning, this might be applied with the zero shot to new cancer, but also this platform is also allowing to gather more and more data, even from different kind of cancer or from new treatment, and this can be somehow improving the overall method generalization capabilities. And finally, well, I'm from the computer science and specifically from the reinforcement learning field. I would also like to understand how the treatment are behaving with respect to the patient on a long term. So I would like to find not just a single treatment, but a part of treatment which is improving overall the life of the patient. And for doing that, we started designing somehow and modeling the life of the patient as a Markov decision process, and so to start understanding exactly how we can apply reinforcement learning technique in order to improve the overall life of the patient. So I would say that this is clearly an ongoing process, but this will get us to the sky, and hopefully before, well, no, not hopefully, I'm sure, before the end of the project, we will get to something that will be released and also will be available to all the clinical centers in Europe. Clearly, this is not just my work, it's the work of a large team, so I need also to thank you, all the other people contributing to this project. 3, 2, 1, yeah.
Thank you. We discuss it at the end.
Thank you. Thank you, Monica. It's my round to introduce next speakers. So with pleasure, I invite for the next talk a close collaborator of Dr. Saad Shaleb from MSK, is Dr. Kevin Boehm, who will talk us about the integration of hematoxylin and eosin wool slide images with targeted DNA sequencing for tumor subtyping. Thank you very much.
Yeah, thanks so much for the introduction and for having me. Really great to be back here in Milan. Thanks also to the tireless audience for staking it out so late into the Friday afternoon. Let's see if advancing the slides is kinder to me than it has been to all previous presenters. Wow, okay. Just as a brief overview, I'll mention this awesome review article by George Ray-Svilho and Jakob from a couple of years ago talking about digital pathology applications focused on you can't see it, automation and biomarkers. And today I'll be talking about applications within the biomarker mining bucket, not automation. So getting additional information out of real-world data that is not typically done in clinical practice. And as one previous example setting the stage, some work by Madison Dharmafal here in the audience, making an ensemble of artificial neural networks to infer tumor subtype from targeted clinical sequencing data and MSK impact, which as you can see in this confusion matrix has very strong on-diagonal performance. And also this landmark study by Alex and Jakob 5 years ago in Nature Cancer, looking at the TCGA in a pan-cancer screen for the presence of phenotype-genotype associations by different subtypes and by different genomic features. So in this talk, I'll be talking about two connected but separate parts, the first of which is inferring granular subtypes from H&E whole slide images, and the second of which is inferring genomic features from those H&E whole slide images conditioned on those granular histologies. I think that's really the crux of what makes part two interesting. And the reason for that is that across different granular subtypes, there are very different prior probabilities of genomic alterations. So for example, in this oncoprint, the first row shows the cancer subtype detailed, with blue denoting high-grade serous ovarian cancer and red denoting low-grade serous ovarian cancer. The row below, the colors are less important, but each occupied spot is a TP53 alteration annotated to be oncogenic. As you can see, those left of the dotted line essentially all have that alteration, and those to the right, essentially none of them have the alteration. So inferring TP53 mutational status from ovarian cancer is actually not a very interesting problem because it boils down to identifying the subtype from the slide. So we'll consider only granular subtypes in this study. A schematic overview of the study is shown here. In a pan-cancer fashion, from the formalin-fixed paraffin-embedded parts, we scanned the H&E whole slide images associated with that part at 20 to 40 times power, and then performed MSK impact sequencing, a targeted clinical sequencing panel of 505 genes. We included 80,000 samples and 400,000 H&E whole slide images. For each of the bags of whole slide images, we passed it through our custom preprocessing package, Muscle, extracted foundation model features, pick your favorite, we used H-Optimus Knot, passed it through our adaptive embedding ontology network, AON, to infer the OncoTree code, or if it was available from a pathologist annotation, simply use the pathologist annotated labels. So for today's results, I'll just show those using the pathologist labeled OncoTree codes. And then inferred genomic properties and tested the inferability of each of those from the H&E. And just a reference, Francisco Sanchez-Vega's talk yesterday. This is part of the MSK Mosaic initiative and will be released in a public-facing portal for academic use. So keep an eye out for that. Moving on to the inference of OncoTree code from H&E whole slide images. Everyone loves a UMAP, so starting with one, this is an embedding of the entire MSK impact cohort at the part level. Each dot is a part, colorized by the ground truth annotated OncoTree code. And you can see substructure, for example, in the bottom left, in the blues, we see the gastrointestinal area. Up to the middle left, sort of at 9 o'clock on the clock, we see that peach color. Those are prostate cancers. We'll take more look at that at the next slide. And then at the top of the slide are kidney cancers and then sarcomas. So looking at those two clusters of the prostate cancer, we tested and found that without any additional training for this task specifically, that one of the clusters was enriched for higher Gleason grade disease, so 8 or greater concretely. Looking at the sarcomas, starting at the top at 12 o'clock, that is chondrosarcoma. Moving down along the manifold, that's osteosarcoma. So far it makes semantic sense that those would be related. Then it moves into that intermixed area in the middle, many of which are unlabeled, many of which are undifferentiated spindle cell neoplasms. Over to the right in the purple is uterine leiomyosarcoma. And then at the probably 2 o'clock on the clock is leiomyosarcoma. So you can see that following along, this is a UMAP just for visualization, but following along the manifold encodes semantic structure. And then looking at renal cell carcinoma, and we see that there are clusters for clear cell on the upper right, papillary down toward the bottom left with Wilms tumor below, and then chromophobe in the upper left, as well as many pluses in gray that denote those that could be labeled no further than renal cell carcinoma unspecified. Applying a nearest neighbors classifier, we label each of those pluses in the embedding space. This is just for the test set. and find that, for example, those reassigned to be clear cell have 41% alterations in von Hippel-Lindau that were annotated to be oncogenic, while those reassigned as a papillary morphology had 0%. Moving next to show the inference capabilities of this H&E-based model AON compared to GDEN's, Genome-Derived Diagnosis Ensemble, Madison's method, we see that performance is excellent overall for both methods. Note that the scale for the AU-ROC on the X and Y axis, the minimum is 0.7, so quite good performance in these 1 versus rest AU-ROC values. But there are some off-diagonal values, and I know there's been a lot of discussion around multimodality. This is one of the motivating rationales for multimodality. When each modality alone has a different pattern of failure, integrating them together can attain overall better performance. And in fact, starting with a very simple late fusion approach, we see that that is in fact the case. On the first row is the H&E-based model, the second row is the genome-based model, and on the third row is the multimodal late fusion model. We see that AU-ROC is excellent for all three, no gains there, but top 1 accuracy is strengthened by the integration of these data modalities. Moving on to part 2 briefly, inferring the genomic features for granular subtypes. Of course, the underlying null hypothesis here is that there is not a pathognomonic feature on H&E associated with a specific genomic feature. And in fact, that's what we expect in most of the cases. This heat map, some of you may have seen at my colleague Madison's poster today and yesterday. It shows each row as a granular subtype and each column as a genomic feature of interest. Without a mouse, a little bit hard to show, but note that there are relatively few dark red hits denoting strong phenotype-genotype association in the test set. And looking at this as a pie chart and a waterfall plot, we can see it a little bit more clearly. Note how the wedge denoting AU-ROC above 0.9 is a tiny fraction. Oh, thank you for turning that on. Will this work though? Oh, thanks. Are you moving my mouse up there? Okay. Thanks. This wedge here, note how narrow it is of the pie. So most of them actually have relatively low phenotype-genotype association, even when non-random. And conditioning on the specific associations actually abrogates many of the reported phenotype-genotype associations. So though aberrations in multiple endocrine neoplasia, 1, are associated with phenotype across all pancreas histologies, if you look simply at pancreatic neuroendocrine tumors, the relation is actually no different than random, accounting for 95% confidence intervals. And something similar is seen in CDH1 alterations in breast cancer, taken in the aggregate, compared to invasive lobular histology alone. Benchmarking against Jakob and Alex's work from 2020, we find that there's an increased area under the receiver operating characteristic curve with this new model, which we have dubbed Paladin. For example, STK11 oncogenic alteration inference in lung adenocarcinoma AU-ROC increases from about 0.62 to about 0.92. And this really nice ablation analysis that Marta Ligero Hernandez did shows that it's really dependent on data set size with asymptotic but continuous gains, for example, from EGFR or oncogenic alteration from 0.62 to with 250 positive examples using our model up to 0.82, and then up to the full number of positive examples, 900, up to 0.87. We're in the process of analyzing the cases in which the genomic sequencing and the H&E-based variant calls disagree. Shown here is the probability of FGFR3 alteration inference from the H&E for the test set, with FGFR3 oncogenic alterations shown here with some gaps explained by HRAS alterations, which is a known phenotypic correlate in bladder urothelial carcinoma, and others without an explanation. So we would expect to see Raynaud disease in a papillary phenotype in FGFR3 altered disease, which has been previously reported, which we do. And then have also taken a look at bulk RNA sequencing from the TCGA test set and found that there's an association even in the non-impact called FGFR3 altered cases of having significantly increased FGFR3 expression. In conclusion, inferring granular histology from H&E can be accurately done across 160 granular oncotree codes, and it refines specific histologies as more granular subtypes. I showed an example in renal cell carcinoma. We've seen this in other histologies as well. and integrating genomics-based and H&E-based calling of subtypes strengthens confidence and accuracy. For calling genomic features from H&E, most genomic features are not associated with a pathognomonic correlate on H&E, which is what we would expect. About 4 or 5% do have an associated correlate. Some of those previously reported in the literature are confounded by granular histologic subtypes. Size of training data, as will come to no surprise as anyone in the room, matters. And there's some association, although we're still investigating this, that the disagreements with DNA sequencing might be informative when called for pathognomonic phenotypes. I have a lot of people to thank here on the slide, as well as funding sources. I'd like to especially thank my mentors, Sarab and Francisco, my collaborator, Madison, and Nikki and Arfat. Thank you.
Thank you very much, Kevin Boehm, for the presentation. And I introduce the last presentation of this session, selected as third best oral communication from Cristina Maria Licciarello, who works at Polytechnic of Milan, the same department of Alessandra Petocchi, and the title of her presentation is Multimodal CAF Analysis as a Pre-Screening Tool for Lung Cancer Detection. Thank you very much.
So good afternoon, everyone. Thanks for having me. I'm so honored to be here today to talk about our work on the use of AI for lung cancer detection through CAF analysis. This is a study developed with the HydraLung project. So we know that lung cancer, and particularly non-small cell lung cancer, is one of the most deadly forms of cancer globally. Its early detection is really difficult, so most of the cases are identified at advanced stage. Even if low-dose CT scans have improved early detection, their high-cost radiation exposure makes them impractical for a widespread use. Moreover, they mainly focus on smokers, leaving out many individuals at risk, like non-smokers or those exposed to air pollution. So we need a pre-screening tool who could be more efficacy and who could expand the early detection. Sorry. So here is where CAFs come to play. We have seen how during COVID-19 years, CAF was successfully explored as a digital biomarker for respiratory condition. But in non-small cell lung cancer, where it is a prevalent and common symptom, it has not yet been explored. So in our project, we thought of using AI to explore the potential of CAF as a digital biomarker to distinguish between non-small cell lung cancer patients and healthy individuals. So I will present first how we collect the data, then the analysis part, and then our results. So we collected audio samples from 109 healthy individuals and 91 stage 3B and 4 non-small cell lung cancer patients who were treated with immunotherapy at Istituto Nazionale dei Tumori. We collected audio samples using everyday smartphone through a mobile app developed by the HydraLung team. So this is a small example of how the app works. And after you record the CAF, it will ask you some questions about, for example, if you have any breath left. So let's have a look at the demographic distribution of our data set. We can see for the age, we have imbalance with the cancer group being much older than healthy groups, with a median age around 17 years old, while for the healthy group, we have median age around 45 years old. Also for the sex distribution, we have a prevalence of female in the healthy class, while a prevalence of male in the cancer class. While for the smoking status, we have a prevalence of smokers in the cancer groups, while a prevalence of non-smokers in the healthy groups, which I think reflects most of the statistics about lung cancer. So what we did was first to apply an automatic segmentation algorithm to extract just the most relevant part of the cough sounds in each audio. We then extract two types of features, 39 standard acoustic features, both in time and frequency domain, and MEL frequency spectrograms using 128 MEL bands. So spectrograms is a common way to represent audio in spatial representation. So we trained a convolutional neural network with the spectrograms extracted, trained in distinguish between non-small cell lung cancer and healthy individuals. We then extracted the 1024 embeddings from the network, reducing them in dimensionality using principal component analysis and preserving 98% of variance, so leading to a total of 20 components. We then concatenate the two type of features, performing a early fusion type of multimodal. So we then split our dataset into 60% for train, 30% for validation, and 10% for test. We applied feature selection algorithm like lasso to select just the most relevant feature from our dataset to of course get the best performance. We perform hyperparameter tuning on the holdout validation set to choose the best set of hyperparameter for our model, and we finally evaluate the model on the test set. So we compared the three models, the unimodal acoustic machine learning model trained just on the acoustic feature, of course, the convolutional neural network trained on the spectrograms, and the multimodal model trained on both type of features. And we compared the results on the test set composed of 22 samples. So we can see of the machine learning model, the acoustic machine learning model performs good with a F1 score of 71%, a sensitivity of 73%, and a specificity of 69%. Remembering that with sensitivity, we intend the ratio of lung cancer patients correctly identified, while for specificity is the ratio of healthy individuals correctly identified. Then the convolutional neural networks performed better with a F1 score of 86%, a perfect sensitivity, and a specificity of 75%. But the multimodal model outperformed both, achieving a F1 score of 95%, a perfect sensitivity, and a specificity of 92%, showing how combining the both type of features help the model generalizing and understanding better the patterns from both cancer classes and healthy individuals. So let's give a look at the confusion matrix of the multimodal model. We can see how we don't have any false negative, while we have just one false positive. And in this context of pre-screening, it is more important to have false positive rather than false negative, because missing any real cancer classes could be really dangerous. So, of course, this is a preliminary study conducted on a small data set, and we will try to increase our data set across age, gender, smoking status, and also stage disease, because we are focusing on late-stage disease. But we have seen how CAF has the potential to become a biomarker to distinguish between non-small cell lung cancer patients and healthy individuals, leading potentially to one pre-screening tool who could be non-invasive, radiation-free, easy to deploy, and accessible to everyone. Thank you.
Thank you very much, Christina. Stop, please. Thank you for your presentation of these promising results. I would invite Arcela to award Christina with the best oral presentation, the third best oral presentation, or Christina, this name, sorry. Okay. I received these instructions, sorry. Okay, I award you with this for the best oral presentation. Thank you very much. Congrats.
I think
so we can open the discussion.
Just for one super quick questions, or I'm sorry for that, but Arcela told us.
Okay, I have two super quick questions. No. May I? No, one. Choose one. one for Christina and one for Kevin. For Christina, just the percentage of adherence to the protocol. All people answer to use the application without any screening failure.
Sorry, can you repeat?
Did you have a total adherence to the protocol, to the usage of?
Yeah. For the people that we screen, yes.
Yeah, good.
Yeah. But maybe not all of them answer to the question because they experience no breathless, for example, or other symptoms. So, yes. But they, of course, we collected all the audio from all the patients that we have.
How many answered? How many not?
I don't know. Like, I think that 7% of them answered.
Okay, thank you. And quick for Kevin, the cutoffs between whole genome sequencing and MSK impact target sequencing in the association with hematoxylin and eosin, I guess is related to AI-driven purposes or clinical purposes. Have you tested both?
Sorry, I'm not sure I understood the question.
Sorry, it's too difficult. Sorry. I guess that you also tested whole genome sequencing approach in the correlation with hematoxylin and
Whole
eosin.
genome?
Whole genome?
No. No, we didn't.
No.
Yeah.
Okay.
I wish we'd had, but no, not yet.
Why did?
Because at our institution, we routinely only get the 505 gene panel. So we can call some features outside of that, fraction of genome altered, for example, whole arm chromosomal deletions, but yeah, unfortunately, we don't have whole genome sequencing for the same scale.
Okay.
Yeah.
Thank you.
Yeah.
So, congratulations to everyone, you survived. We are now at the last level, and then we are ready to talk about the best posters and awards.
Okay, just to summarize, there were different categories for abstract submission, and about 50 abstracts have been submitted. External reviewers evaluated this abstract by assigning a score to reviewers for each category, and I think we can see here the names of the external reviewers, no? There should be a slide. No? Okay, go. Of course, the process was blinded, so external reviewers had only access to title and text of the abstracts to guarantee the maximum transparency. So the best 3 abstracts were selected as best oral, and we have already heard of them during the meeting. Then among the others, 42 abstracts were selected for poster presentation, and among them 4 were selected to be awarded. We will have the 2 top abstracts, 2 top posters that will be awarded with a prize worth 500 euros from Artificial Intelligence for Oncology. And also, in addition, 2 other posters will be awarded with a prize of 250 euros sponsored from Molecular Oncology Journal. Maybe there is a slide for Molecular Oncology Journal. So now we can go on with the prize giving.
Thank you for Arsi for the great event, and thank you for all the people strong and brave that are still here. And it's the moment to award the poster number 4 from Dresden, Germany, Michaela Unger, and the title of the abstract is Deep Learning for Biomarker Discovery in Cancer Genomes. The poster number 3, the award of the poster number 3, is for Alice Andalo, from Istituto Romagnolo per lo studio dei tumori Dino Amadori di Forlì, Cesena. The title of the poster is Patient's Perception of Artificial Intelligence and Data Protection in Healthcare, a survey for an Italian cancer center.
For the second place, Dr. Lorenz Schachtach from Dresden, Germany. The title is Predicting Clinically Actionable Biomarkers from Incomplete Patient Data Using TB-PFN.
Okay, and the top one abstract was from Federica Corso from Molecular Oncology Department of Fondazione RCCS Istituto Nazionale dei Tumori, benchmarking large language models for data retrieval in clinical trials, the Apollo 11 trial data for advanced lung cancer patients.
So now is the time for the real final boss from Marcela. Now it's your turn to close our works.
So, as usual, as everywhere, I'm very brief in my parting words. Okay, so the slides, I just wanted one slide because obviously this year was very special. So we launched the new Society of AI in Cancer Research, and I just wanted to use this moment to remind me, we have to remind to everyone, please, for who that yesterday couldn't make to be member of the society, please be member. We don't have the slide with the QR code, okay, it's coming. So, while the slide is coming, thank you very much again. It has been, especially for you that remains until the end. This year was, let's say, very different compared to the others because we have seen all together how much we have grown. And I think that is the, it's nice because it's an ending story for me. I mean, I will not be anymore my Congress, so that it finished. But I am happy that this history and this collaboration will continue because next year will be, I hope, big story because probably not hosted here anymore at Istituto Tumori because we are becoming bigger and bigger. And since next year, I wanted also to remember on 7 and 8 May 2026. So can you launch save the date before and then we'll go back? Okay. Put these dates already. You are all invited to submit. And this will not be, as you can see, anymore. Let's say I put it the 4th edition, but just to remind that was an historical moment for us, for all our friends. However, this would be officially the first annual meeting of the ESAC Society, and I invite you from now to participate. We'll be again, just to maintain a bit the tradition, in Milan, and then, I don't know, for sure, in the next years we'll decide in another European countries. And of saying that, my last thing, I wanted also to endorse a big event that Mireia and Jacob and also that are chairs, but also I'm in the scientific committee and we draft all the program together. Don't forget the ESMO AI, which is a very important educational moment. Would be held it in Berlin, in Germany, 12 and 14 November. And I just saw today the emails. They opened today the abstract submission and will end 2nd of September. So, I mean, I talked with some friends. This was just a kind of pre-event before also when we go and meet together all in ESMO again. Of saying that, now back to my last slide. So don't forget to be members. You can, let's say again, see the QR code. So my only take-home messages are, as usual, keywords. So for me, I'm saying this keyword, repeating in the 3 years, and I'm going on to repeat it. So the education, it's a key to understand, to adapt, and also to implement AI. So for sure, this year we have seen more and more usability and implementation. The second keyword, which was already mentioned, is collaboration. And collaboration, I totally agree that collaboration couldn't be anymore within the same institution. Can have to be absolutely among different institutions, but also now more than ever among company, industries, even because, for example, Sophia Genetics in this case is a company that they are doing modeling, okay, also we are doing modeling, but there are the exchange of idea, the exchange of the work can help us to improve what we are doing. So we have to have a more open mind in these type of collaborations. I know that you are all very tired, so thank you again and goodbye. And to go back home, I don't know. I forgot.